Sir, good morning.
Hello, boss. Good morning. Good morning. How are you?
Oh, I am fine. Hello, Professor
Hello.
Jaisankar.
Hello. Hello. Nice to meet you once again.
Yes,
Nice to
yes.
meet you.
What is the time now in US?
It is 11 o'clock in the night.
Okay, okay.
Hi, Dr. Jaisankar, how are you?
আরে ভালো ভালো, how are you?
ভালো আছেন?
খুব ভালো আছি, খুব ভালো আছি। আপনি কেমন আছেন?
এই তো চলছে।
Great, great, great.
So, Professor Alokesh Bisai from IISR Kolkata, he has already joined. Dr.
Hello.
Tanmoyee Bhattcharjee is there. And Professor Sunil Tolapatra also is there. Professor J.K. also is there. And the principal, sir, of Midnapore City College, Professor Sudipta Chakrabarti also is there. And Professor Prasenjit Mal from NISER Bhubaneswar, I can see him.
Yeah, I'm here.
All right. So it's a very close circle.
Not a heterocycle. All are organic chemist also.
Yes. Dr. Abhishek Ghosh also is there from Midnapore City College. I can see him.
Yes, sir.
Okay. Professor Sunil Tolapatra has joined for the first time in our webinar. Yeah, I can see Professor Dilip Kumar Maiti. Dada, ভালো আছেন?
Dilip da. So he's enjoying the rain probably. Dilip da.
I think we shall start now because I think it is time already.
Yes.
Good morning.
College.
Good morning, Dilip da.
Very good.
2 minutes we shall start, isn't it? Madam, how do you say?
Yes, sir. Can we start now?
Maybe in 2 minutes, so let us introduce ourselves. Yeah, it's okay.
Yes, of
And
course.
Prithidipa is also here. Prithidipa.
Yes, sir. I'm right here. Good morning, all of you. Good
Yeah,
morning.
good morning.
Good morning.
Good
Good
morning.
morning,
Good morning.
Prithidipa.
Yes, thank you, sir.
Professor Jaisankar Roy is there from Kharagpur.
Yes, sir.
Sir, namaskar.
Good morning, Professor Ray.
স্যার আপনার শব্দটা কোনো রকমে আসছে না প্রফেসর রে
Maybe the poor internet connections is giving the trouble. Is it so, sir?
প্রফেসর সুনীল কুমার তলাপাত্র স্যার আপনি একটু আনমিউট করে 1 মিনিট কথা বলে নিতে পারেন এই সময় প্রোগ্রাম শুরু হয়ে গেলে আর কথা বলা যাবে না
Maybe Professor Prasenjit Mal, you can switch off your fan or the mic.
So Tanmoyee madam, maybe you can start now, isn't it?
Okay, sir. Good morning, everyone. Good morning, excellencies, dignitaries, and all the participants who are present here. It gives me immense pleasure to extend to you all a very warm welcome on behalf of Chirantan Rasayan Sanstha and Midnapore City College, who have clubbed all of us to today's webinar, Science Beyond Boundary, Invention, Discovery, Innovation, and Society, Rasayan 9. The COVID-19 pandemic has created the largest disruption of education system in human history, affecting nearly 1.6 billion learners in more than 200 countries. Closures of schools, institutions, and other learning spaces have impacted more than 94% of the world's student population. This has brought far-reaching changes in all aspects of our life. It has changed the way we do almost everything. There is significant hope that this is temporary. But while we continue to live under various lockdowns and restrictions, how can we carry out further research? Because the pandemic, ever since it started, has curtailed the pre-existing normalcy. Trace. Can everyone hear me? Is there any problem, sir?
No, it's okay. We can hear
No,
you.
it's fine.
No,
fine.
please continue.
Okay. So academic interaction has also been hampered to a great extent due to this situation. So the need of the hour is to innovate and implement alternative strategies. As an instigator of that spirit, the organization Chirantan Rasayan Sanstha, in association with Midnapore City College, has decided to host this international level webinar to motivate the young upcoming researchers to continue their quest in spite of all odds. That is why today we have assembled via Google Meet platform with live coverage on YouTube. So now let us have the pleasure of listening to the Enchanting Prayer for initiating our webinar. I'd like to request our vocal performer, Dr. Prithidipa Sahoo, faculty member of Department of Chemistry, Visva-Bharati, Shantiniketan, to perform the invocation. Prithidipa ma'am?
Yes, thank you, ma'am. Sangachadhvam sangbadathvam sangbomana sijanatam sangachadhvam sangbadathvam sangbomana sijanatam. May we march forward with a common goal. May we be open-minded and work together in harmony. Samano mantra samiti samani samano mantra samiti samani samanam mana sahachita mesha. May our prayers be one. May we belong to our one brotherhood. Anandaloke mongola loke birajo shotto sundaro মহিমা তব উদ্ভাসিত মহাগগন মাঝে বিশ্বজগত মণিভূষণ বেষ্টিত চরণে আনন্দ লোকে মঙ্গলা লোকে বিরাজ সত্য সুন্দর বিরাজ সত্য সুন্দর Thank you all.
Thank you, ma'am. Your voice was just so mesmerizing. I think we just had an heavenly experience.
Thank you so very much. Thank you for
Really,
your
ma'am.
kind words.
Your voice was really so mesmerizing, ma'am. Thank you, ma'am, so much.
Thank you.
So now I'd like to request the president of the society, Chirantan Rasayan Sanstha, and also the convener of this webinar, Professor Braja Gopal Bagh, to kindly deliver the welcome address. Before he starts, let me briefly introduce Professor Braja Gopal Bagh. Professor Braja Gopal Bagh did his Masters of Science in Chemistry from the Indian Institute of Technology, Kharagpur, and got his PhD from the premier research institution, the Indian Institute of Science, Bangalore. Then he moved to Germany with the prestigious Alexander von Humboldt Fellowship and spent 4 years in Ruhr University, Bochum, Germany. Then he came back to India and joined the Vidyasagar University as a reader in the year 2000, and where he became full-time professor in the year 2008. Along with teaching, he has devoted his life for research in diversified research areas such as plant metabolites as renewables, nanochemistry, advanced functional materials, targeted drug delivery, etc., in addition to the main field, organic chemistry. He has already produced 18 PhDs and published over 70 research papers in leading journals and delivered over 80 invited lectures in India and abroad, including invited lecture presentations in the symposium organized by IUPAC. Based upon his academic achievements, the Ministry of Human Resource and Development recognized him for the leadership for Academicians Program LEAP India in the year 2019, jointly organized by ISER Kolkata and Harvard University, USA. He is the founder president of CRS, and he is also the editor-in-chief of the Society Journal. So, with this brief introduction, I'd like to request Professor Braja Gopal Bagh sir to say a few words about the society.
Thank you, Dr. Tanmoyee Bhattcharjee, for your excellent introduction. Honorable Chief Guest, former President of the Indian Chemical Society, Professor Sunil Kumar Tolapatra, Honorable Principal of Midnapore City College and also the co-host of RASAYAN 9, Professor Sudipta Chakrabarti, former CRS medal awardees present here today as guests. Today's recipients of medals who will present their award lectures in RASAYAN 9, Professor Alokesh Bisai, Dr. Mayuri Napagoda, Dr. Subhasis Roy, their chairpersons, Professor Jaisankar Roy, Professor Dilip Kumar Maiti, Professor P. Jaisankar, Dr. Abhishek Ghosh, and overall coordinator, Dr. Tanmoyee Bhattcharjee, faculty members, research scholars, master and graduate students from various institutions present here today, ladies and gentlemen. It gives me an immense pleasure to welcome you all to today's webinar entitled Science Beyond Boundary, Invention, Discovery, Innovation and Society, RASAYAN 9. Let me tell a few words about our society. Chirantan Rasayan Sanstha was established in the year 2016 with the following objectives: to promote research and development in all branches of science for a better living, to organize seminars, workshops, training sessions, and similar activities for the promotion of research and development in all branches of science and outreach activities, to collaborate with established institutions and other scientific societies in India and abroad so as to fulfill the goals, and to carry out activities that may assist in or be necessary for the fulfillment of the above objectives. Since its inception, the Society organizes various symposia, webinars, and so far 8 symposia and webinars have been organized starting from 2017, like RASAYAN 1, 2, 3, 4, 5, 6, 7, 8, and this is the 9th one. The Society also honors eminent scientists and academicians by the presentation of CRS medals, and since the year 2017, we can see more than 20 recognized academicians and scientists from over 6 countries have received CRS medals, and they have presented award lectures on various occasions, so as you can see here. And in the year 2021, this is ongoing. Already 8 people have
মুশকিল হচ্ছে আমার এখানে কোনো প্রেজেন্টেশন হচ্ছে না, কোনো সাউন্ড নেই, খালি ছবি আর কিছু নেই, সাউন্ড নেই। না না, আমার মনে হয় আমারটা কোনো প্রবলেম হচ্ছে। তুমি একটু ব্রজকে বলো তো, ব্রজকে ফোন করে পাওয়া যাচ্ছে না। ব্রজকে ফোন করেছি, অনেক চেষ্টা করেছি, হয় না, যাচ্ছে না। হ্যাঁ, না আমার
Can you hear me?
Yes, sir, we all can hear you.
Okay.
Yes.
Good afternoon. So, in 21, already 6 persons have got medals and they have presented their award lectures. And well, in addition to all those, the Society also publishes a open access journal, RASAYAN, whose English name is Applied Chemistry and German translation is Angewandte Chemie. It is a quarterly open access peer-reviewed journal where publication is free of charge, and the articles are also downloadable free of charge. It has got ISSN, and recently we have become the member of Crossref, and all the articles are checked by Authenticate, and also it publishes articles, suffice to mention, on science beyond boundary. Well, students are the future leaders of science, technology, and society. Hence, we try to keep a program for the students called Students Corner. And we encourage student-scientist interaction, chemistry quiz, felicitation of school toppers, demonstration of food processing, preservation, and packaging, and so on. And here, as you can see, the star holders in Madhyamik and HS, they are being felicitated. And also, I was fortunate to participate in the Leadership for Academicians program, Leap India 2019, organized jointly by IISc Calcutta and Harvard University. So among various interactions at Harvard University, we are looking around the campus. So this is the Harvard University campus, and that time there is full of snow. And this particular statue drew our attention. This particular statue was gifted by the President of Ireland. And on the other side of the statue, you can see there is a quote that never again should people starve in a world of plenty. So keeping this in mind, the society also started distributing food and other materials during this pandemic period when people are in distress. So as you can see, people are collecting materials. And also keeping the students' sufferings in mind, we organized a program called Lab on Wheels. This was one innovative workshop in blended mode where the students could assemble keeping the COVID protocols in mind, and they could carry out even some work in one-day trip. Well, how the name is Science Beyond Boundary, Innovation, Discovery, Innovation, and Society. In my feelings, if we have to start the society, only invention and discovery, these are not enough. These are the primary things, but there has to be innovation to reach the society. And that is how we have given the name for this webinar series. And I am a student of chemistry. And since school days, I learned basic science, and then during graduation, chemistry, and then in MSc, organic chemistry. And then while teaching, I try to touch various areas which are given here, like some about 2,000 areas and so on, and these are flourishing. Well, it is true that if one has to investigate in depth, then one has to focus on a particular area. But unless there is cross-border interaction beyond boundary, we will not be able to serve the society. And that is obvious from the recent Nobel Prize given in chemistry. And the reason was for the development of a method for genome editing, genetic seizures, a tool for rewriting the code of life. Well, keeping those in mind, always we try to keep the speakers in such a way that we get a field for the developments in different areas. And today we have speakers who will touch hardcore organic chemistry, synthetic chemistry, and then biology, and then advanced materials, and so on. So we look forward to that. So let us recognize the potential of ours, ideas and sharing knowledge, coming up with newer ideas for the benefit of society and mankind. Let us make this symposium, Science Beyond Boundary, Invention, Discovery, Innovation, and Society, RASAYAN 9, a grand success. Thank you very much. Namaste. Thank you.
Thank you, sir. Thanks a lot, Professor Braja, for your wonderful speech. Sunil sir, kindly can you mute your... Thank you, sir. Thank you, Professor Braja, for your wonderful speech, which establishes the main underlying theme of today's program. Now I'd like to invite Professor Sudipta Chakrabarti, Principal of Midnapore City College, to kindly deliver the welcome address.
Thank you, Professor Bag. Good morning. Myself, Dr. Sudipta Chakrabarti, Principal of Midnapore City College, which is established in 2017 in a premier area of Midnapore, actually, Gangal Mahal area, and it is set up by Moraine Human Research Development Organization with our founder director by Dr. Prithidipa. I am honored and glad again to be a part of this international webinar on science beyond boundary, invention, discovery, innovation, and society, RASAYAN 9. I am grateful to represent our college again. Midnapore City College has earned some prestigious milestone within this very small time frame. Recently, we have achieved 7th rank in West Bengal and 41st rank in India in Education World Non-Autonomous College State Ranking 2020-21. It is the result of our hard works in the academic and research field, and it has given further boost to our growth. I am certain that the webinar will act as a catalyst to stimulate the growth, and in this regard, I would like to thank and welcome Professor Alokesh Bisoi, ISIR Kolkata, West Bengal, Professor Dr. Mayuri Nagapada, University of Aruna, Gali, Sri Lanka, and Dr. Subhasis Roy, Beats Pilani, Vidla campus, and Dr. Jaisankar, and Dr. J.K. Rai sir, and Dr. Dilip Maiti for their precious presence among us. Finally, I am concluding my speech, wishing a enriching session. Thank you, Dr. Professor Bag, and thanks to all.
Thank you, sir. Thank you for sharing your valuable information with us, and thank you for sharing your kind words with us. So now, let's move to the scientific program. In this session, we have 3-hour lectures. The first hour lecture will be delivered by Professor Alokesh Bisoi, ISIR Kolkata. Professor Dilip Kumar Maiti from Calcutta University will be the chairperson, while Professor Alokesh Bisoi delivers his hour lecture. Professor Dilip Kumar Maiti, over to you.
Unmute, Dilip, unmute yourself.
Sir, unmute yourself, Dr. Maiti.
কথা শোনা যাচ্ছে না তুমি বোধহয় বুঝতে পার হ্যাঁ
May I audible?
yes now you are audible.
Yes.
Okay, so very good morning. And I'm thankful to the organizer for inviting me to chair this session. So let me introduce Professor Subhasis Roy. Professor Roy is from IJR Kolkata, and he is Professor, Department of Chemical Science, IJR Kolkata. He did MSc at BHU, Varanasi. He did PhD at Kanpur and postdoc at UC Berkeley, California. He joined as assistant professor IJR Gopal, and then he became associate professor. And in 2018, he became the professor. And subsequently, he moved to IJR Kolkata in 2019, and he is working over there. His research interest is synthetic methodology and synthesis of natural product and natural extract methodology. He received CRSI Bronze Medal, CRSI Young Scientist Award, lead lecture in Pfizer Symposium at IISc 2016, DST Young Scientist Research Grant, BRS Young Scientist Award. He held different positions, and one of the important positions is the Dean of the Faculty Affairs, IJR Gopal. He delivered different lectures in international fora, like in USA, Germany, and UK. One such is Flowhead Conference, University of Florida, USA. With these few words, I invite Professor Roy to deliver his lecture. Professor Roy, please.
Good morning, everyone, and thank you, Professor Maiti, for your kind introduction. And at the outset, I would like to thank the convener of CRS, Professor Gopal. I also thank our principal, Midnapore College. I'm very much happy to be here because my excitement because I am a student of Midnapore College. Can you see my slide?
Yes.
Yeah, okay. So the reason I am more excited is that I have done my BSc in the year 1995 in 1998 from Midnapore College, and the CRS is somehow attached with Jaisankar University as well as Midnapore College. So I'm really very much excited actually for this opportunity, and thank you for this award. Also good morning to Professor Talapatra, Professor Roy, and other dignitaries. So I would just like to start my lecture, and I think I have given 50 minutes. So I think around 45 plus 5 or something like that. The time limit is 45 plus 5 or anything, Dr. Maiti?
It's fine.
Okay.
Go ahead.
Okay. Okay, so as you can see, the title of my talk is the architecturally interviewing alkaloids as a platform for the discovery of novel methodologies and total synthesis of alkaloids. Now the question comes, why alkaloids? Why architecturally intriguing? And why there is a need for discovery of new methodologies? So this slide gives many questions to the audience, particularly students. I will be more interested to interact with the student in this talk. And again, for the interaction with the student, so I just want to know, as a student, I would like to know why I should worry about, synthesis of natural product. So the inspiration and motivation for our group is, we just simply, try to understand the nature, because what we believe is that biology is nothing but chemistry. In chemistry, we do everything in a confined laboratory, but nature is doing things. So for nature, whole laboratory, whole universe is nothing but laboratory. So basically, what we believe is that if we understand correctly the basic principle of chemistry, and if we can connect, if we know how particularly nature is making natural product or any secondary metabolite for that matter of fact, we should be able to devise new strategies, maybe unified strategies to natural product. So definitely for a synthetic organic chemist, normally the goal is drug discovery or something to do for the benefit of the society. So if you look at the drug discovery program, and this slide gives the answer why natural product. If you look at 60% marketed drugs are natural product or inspired by nature. Now why? As a student, I would always ask and would like to know why exactly natural product. The simple fact is that nature's beautiful way of synthesize and metabolize an organic molecule, thereby bond breaking and making is the most important phenomena in nature, and that is nothing but it is homo and lumo interaction. Just to give you one example, nature's beautiful way of synthesizing glucose through D-fructose via Amadori rearrangement. Not only nature synthesizes it, also she knows how to break it down, degradation. Again, through retroaldol, so breaking into 3-carbon unit. And there you will see this mechanism, enamine catalysis. Nature is doing long back, starting this when it started universe. And that is the idea actually taken by scientists. And in 2000, if you recall, it started enamine catalysis. Although the original idea started in 1970s by Hajos Paris and other guys. But the idea how nature is making molecule, that has been realized for making Hajos Paris ketone. And that particular area actually, again in 2000, it had like mushrooming effect leading to number of papers. So what I mean is that enamine catalysis itself is a nature inspired method. We learn from nature and we have done that. So similarly, if you look at fatty acid synthesis, the reason I'm saying nature is the guiding us. Okay? Look at the fatty acid synthesis starting from acetyl coenzyme and its degradation. Okay, so basically nature knows how to make it and how to break it. And if you look at the principle of drug discovery, it mostly follows ADME principle. And in ADME, absorption, distribution, metabolism, and excretion. This third term, M is very, very important. That is where, drug discovery fails many times because we make molecule, but biological system must know how to break this molecule. So various strategies has been developed in drug discovery. This is what I was telling you, the ADME principle. So that means the drug discovery, we can just simply think that a drug is nothing but a foreign molecule, goes into the biological system, it start action, then break into pieces, remove from the biological system as quickly as possible. Otherwise, it will do again binding. Why again? This binding, receptor bindings are nothing but electronic guidance. That also tells us why heteroatom is important in drug discovery. Why one should worry about natural product having number of heteroatoms. Why it also tells us approximately 50% drugs are nitrogen content. So with a very simple fact that nitrogen being the less electronegative than oxygen, it would definitely act as, the partner of HOMO by delivering its electron pair. So this is nothing but it should look like a catalyst. It goes action done and it should be removed. Not like an inhibitor who takes part in the reaction, leads different product and leading to a lot of side effects. Now if you look at the better drug criteria, it should be heterocycle, we understood, but with three-dimensional architecture. It should not be a flat molecule or planar heterocycle because it would do unselective binding with the receptor. So what I mean, just for student, benefit of student, what I mean is that if I need, let's say, imidazole is a small molecule responsible for something, I should not take imidazole, but rather I should take L-histidine, where I have imidazole linked with alpha amino acid, in fact, which is the one of the partner in the protein. In many proteins, you will see that alpha amino acid like histidine or tryptophans are present. So what I mean, three-dimensional architecture required for selective binding with the receptor. Therefore, chirality is the most important factor. And this also give you the idea, thalidomide strategy. Okay, even a particular enantiomer is required, not the other enantiomer. So basically, if you look at all these areas and all these basic, stories, it clearly tell us if it is natural product derived drug, since nature knows, because since nature has made that natural product, probably nature also knows how to break, how to metabolize that partner with three-dimensional architecture. Now, not only natural product, when people isolate natural product, it has to go through various reactions. Like let's say isolation chemist, takes some natural things, let's say, some species, and then they extract. This extract itself is nothing but many chemical reactions. Therefore, many times we will see that natural product, the one we have made, is not good one. It's not showing the reactivity or activities. Why so? That is simply because of when we isolate them, we also do a lot of basic and acidic workup. Therefore, we also break many bonds. Maybe this particular natural product is the conjugate of, something like glucose or some other small molecule. But while isolation, we go through some acidic or basic workup or, reactivities. Therefore, it breaks those functionality, which might be important for the biological activity. Therefore, there is another area where people make natural product derived, derivatives. Like in this particular slide, you can see that Gao et al. In 2018 had shown that it is not the natural product, sarcoidine G, rather its derivative, were found to be shown better activity. And they have actually, published in 2018. So with this in thought, our group is working the natural product, particularly alkaloid. So if you look at this slide, I have just summarized some of the interest, some of our group interest. So the interest we have taken because of, not only because of their architecture, but also their biological activity, as well as, some synthetic elegance we also require to make them. Can you hear me?
Yes,
Yes. Continue,
Okay.
please.
Okay, thank you. So now, if you look at the silabinolic acid, it is nothing but a cyclopentane alkaloid. Start, and then you see that this is coming from a tryptamine. This is nothing but isoprene unit, and this is coming from alpha amino acid. Look at glycilamine, which has been synthesized from our country by Professor Pandey. If you look at, this is nothing but a structure having emerald alkaloid, where this isoleucine is attached. Leucine is attached. Dihydroxyclican is nothing but a rearranged structure of this. Now it also attached with tryptamine. So they are nothing but conjugate of a particular alkaloid, and again conjugate of other alpha amino acid or an amine derived from decarboxylation of alpha amino acid, like tryptamine. In this particular case, it is tryptamine. We are also interested for this kind of alkaloid, benzophenanthridine alkaloid, which is now linked with sesquiterpene. And our group is also working on this kind of molecule, peroxicone, which is nothing but a triterpene coming from a combination of isotexine diterpene linked with a monoterpene like geranyl pyrophosphate. So these are the other alkaloids like lysergic acid and cycloplasmin. These are the other class of alkaloid, and also we are more interested for this kind of architecture like chimonanthin or folic anthin having two pyrroloindolin links at the pseudobenzylic position, thereby creating 4 stereogenic center in contiguous manner. Even if you go further, it is ditryptophenylene is having now ditryptopiperazine attached to this kind of structure. Now, if you look at calicanthin, is nothing but an isomer of this, structural isomer of chimonanthin. There are other molecules like quadrizoline C. You will see there are 4 pyrroloindolin linked in various patterns. Now, as this is the structural isomer of chimonanthin, this particular portion also can get rearranged to give this kind of structure, leading to another natural product called cytolin. We have also contributed in some extent to area where terpene-based chemistry, and we have recently shown that synthesis of alcohol, and currently we are working towards this natural product. In 2015, we have just shown natural product like thionaquinol F, which is having ABO skeleton. So these are coming from diterpene-based biomimetic biological pathway. But if you look at this molecule, which is synthesized by Professor Govardhan Mehta in 2006, the classic molecule merylactone. The reason I am trying to show you this molecule to the audience, particularly student, if you look at this particular structure, looks like very compact and very small. But actually, if you look at the element present and the stereogenic center present, look at here, this is having vicinal all-carbon quaternary stereogenic center. There is another all-carbon quaternary stereogenic center. And if you look at, there are many stereogenic center in this kind of triquinone. Making them is really a challenge in 2006 from our country. Professor Mehta actually shown that it can be synthesized, although in racemic way. Now, if I look at abetans and dinorabetans, they are having nice tricyclic structure. They are originating from geranyl pyrophosphate through copalyl pyrophosphate. Now, the most interesting thing is that nature is not only making this, but also making like this kind of tetracycle. pentacycle, hexacycle, octacycle, and so on. So therefore, we need to understand how nature is making them. Unless we know how nature is making, probably we won't get a strategy for synthesizing them. And if you look at, these are nothing but a polyencyclization, because nature makes, isoprene. This monomer is IPP, isopentenyl pyrophosphate. Now this is nothing but it will isomerize to DMAPP, dimethyl 3,3-dimethyl allyl pyrophosphate. Now they can combine to give you giranine. Now it will attach with another IPP to give you farnesyl. Farnesyl attach with another one to give you geranyl geraniol. Again it will add to another one, leading to 30 carbon unit, which is nothing but a structure of coelin, and which is the starting point for actually biosynthesis of lanosterol. Again, lanosterol can be starting point for the synthesis of cholesterol and all these steroids. So if you look at this structure, we need to understand the biosynthesis of this natural product. Therefore, the biosynthesis of this polymerization of particularly isoprene is very, very important phenomena. In fact, if you look at the synthesis of IPP pyrophosphate, the first step is the Claisen type condensation. In fact, Claisen has seen this condensation where nature is doing a biosynthetic pathway for fatty acid. Claisen has picked up the first step and did in the laboratory. That is why this name Claisen reaction is coming. Okay, this is again for students, just to motivate them that you could do something new and you can actually do essentially that reaction in your name. Now to do that, you must know how nature is operating. Okay, in today's talk, as I said, that these particular things I will be taking care. Okay, I have already shown you that lysergic acid and clavin, and if you look at the structure, they are having of similar class. And if you look at these simonanthin and calicanthin, by looking at them, you can see that this is nothing but a rearranged structure of this. So therefore, we will follow some sort of biomimetic synthesis towards the end. Now, if you look at the ergot alkaloid brief history, as I said, not only natural product, the synthetic drugs, if you look at pergolides, nicergolin, methargine, they are not natural product, they are actually derived from natural. And if you look at, these are the marketed drugs, like pergolide, Parkinson, nicergolin for used for migraine, methargine to stop the postnatal bleeding. Now, of course, there are other bad effects as well. If you look at LSD structure, this is also derived from ergot. Now, as you know, 1960s counterculture in the those countries. So this is banned. LSD is banned. So therefore, we can synthesize many derivatives, but some of them could be having better effect, could be used for human well-being. Some of them, of course, will have some bad effect. Again, the bad effect actually coming from, again, the interaction is electronic guidance, homo-lumo, same thing. This will be there everywhere. Now, the major idea came in this area because of the structural resemblance of this well-known neurotransmitter adrenaline. If you look at, if you see this indole is aromatic ring, then you see this phenethylamine. So this is nothing but indole and like phenethylamine. Now, broadly, if you look at, they are divided into two different classes: lysergic acid, clavin. Now, what is the difference? The difference is only this carbon. In this carbon, lysergic acid, this is in highest oxidation state, carboxylic acid. But if you look at here, this is in methyl. So this is the reduced form. Now, if you do somehow oxidation, just remove these two hydrogen, maybe probably through this radical pathway, you can just form this carbon-carbon bond leading to cycloclavin. And if you look at the literature, this gentleman is the pioneer who started long back in 1954, 1956. He has given the first of all synthesis of this structural scaffold through a tricyclic ketone, popularly known as Woodward ketone. What he did alpha amination and did a Robinson annihilation type reaction to get the fourth ring. And therefore, many synthetic strategies has been derived from Woodward ketone and another similar type of ketone known as Uhlage ketone. There are many chiral pool synthesis where they have followed an intramolecular egg reaction. These are the asymmetric approaches known till date for this alkaloid. They start with Gardner-aldehyde, glutamic acid, Evans-Ocellari, elements-Ocellari. Daniel Warch had shown no-rich asymmetric hydrogenation to show this kind of structural scaffold. What we thought? Let's come to our hypothesis. What we thought? Can we make this kind of diene ester? Now, these diene type substrates are very, very important. Whenever it's a diene, it always draw our attention towards Diels solder. And we know in Diels solder, it has to be a cis, not the trans, which is responsible for 4+2, which is the partner for which give the homo in normal Diels solder reaction. But what we thought, can we have this kind of diene ester, and can we place something and then try to form the fourth ring in this kind of system? So what we thought, if it can follow 6-endo trick to give this as a Michael, or it could also do simple ester aminolysis to give a mind. But at the end of the day, what we can see that these are of tetracyclic core which can be elaborated. Okay, so we thought that it would be worth testing to such type of reactivities. Now this can be synthesized from this kind of nitro ester, which can be synthesized in turn from this kind of starting material following a catalytic nitronate Michael. So this is where we have developed one methodology where you can see that simple thiourea, which is just commercially now available nowadays. And we have found that this kind of nitronate Michael can happen very nice way to form this carbon-carbon bond. Therefore, we could get this kind of structural scaffold for the synthesis of lysergic acid and other alkaloid. But however, what we have seen, there are a lot of factors that has to be satisfied, like hydrogen bonding effect. This is very important. This R group should not be sterically hindered. There should be stereoelectronic effect, that should be always E, not the G1. And we have to also control the electronics of this nitrogen. So therefore, we have seen electron withdrawing group onto this nitrogen is very, very important. And we have seen that if these four things is satisfied, this should be able to give us the advanced intermediate for the synthesis of this natural product. And we have also seen that since they are the diastereomers, one can actually, to get the minor one just by epimerizing alpha to this nitro position to get SR. Because in ergot, both these syn as well as anti, both are required for the synthesis of other congeners of that particular family. So in practice, what we have seen that we can take this and with this kind of catalyst, we can get 97% of enhancer selectivity. The diastero selectivity was not bad, not good as well. 3.7:1, but however, as we know, these are can be flexible because I can utilize this to reach over there. And similarly, a pseudo enantiomer catalyst gives me this as measure. Now again, since we can convert this to there, so now we have all four types of enantiomer to synthesize all these congeners of this family. And we have what we have seen is that in reality, when it was tertiary butyl, reaction did not happen. We have seen that electron withdrawing group on nitrogen is very much required, otherwise no reaction, and which is simply because of deactivating the LUMO, because of lone pair adding onto this pi star ultimately of this carbon. Now, if you look at this compound, we have just did simple reaction like reduction to get aldehyde. This can be done with one step using diol as well. The target was to make one carbon. from these two carbon, therefore we have followed alpha oxyamination, and then we have oxidatively cleaved to get this aldehyde, which was reacted with stabilized to give this, and this was reacted with formaldehyde and Babco. Initially, we thought we'll stop at, this Belly-Simon product here, CH2OH. However, in the same condition, it's a beautiful thing happened. It gave elimination as well. So what we thought, after having this CH2OH, and since it is tosylated, this particular proton is sufficiently acidic as it is situated at the vinylogous position of this ester. Thereby, it would follow a E1CB to give you this kind of transconjugated diene ester. Now, with this in hand, we came to test this our hypothesis whether it is 6-ended ring or ester aminolysis. We have seen that there was no trace of ester aminolysis. This is only 6-ended ring, where we could get 2:1, where Michael is the preferred pathway. Now we did chromatographic separation, and from there we have synthesized lysergol and isolysergol after the tosylation. Simple reaction. Now the question is that why no ester aminolysis? Why only Michael? This is understood later on that it is anyway alpha beta unsaturated ester. This kind of alpha beta unsaturated ester are highly stabilized. Therefore, this ester aminolysis was not the preferred pathway, although this will go through a trans diene ester. It is preferring a pathway where a cis diene ester. So therefore, in the equilibrium, we have a cis estrans. Now a cis react. Now estrans will come again in the equilibrium. Therefore, all these things will be converted to unireactional way. Then what we thought, can we give a collective total synthesis of this alkaloid? And then we found out that secoagroclavin is the simplest congener for this alkaloid. And all these natural products actually coming from by functionalizing secoagroclavin. So here we asked a question that, can we make this? And then somehow can I do allylic oxidation, a regioselective allylic oxidation, which should prefer here over there. Thereby, I can make this, I can oxidize to give chanoclavinaldehyde. Not only that, so this is very interesting thing. See, normally we know amine and aldehyde having the same moiety will be very reactive. They will form hemiaminal, therefore iminium and inamine. However, chanoclavin 1 aldehyde is a natural product where you will see there are 2 NH, but still molecule is stable. Why? The answer is lying over here. If you look at this stereogenic center, this olefinic center, where it is E. Okay. So now, if this E, if you can make it G, Jusamen, not N-Gagan, A converted to G, then it would actually cyclize. It's like, the chemistry of vision, where retinal will react with rhodopsin, is nothing but again epsilon amine of lysine. It will make a conjugate which is nothing but iminium. It's a alpha, beta, gamma, delta, all these unsaturated iminium, thereby the double bond will be converted to single bond, and therefore it can be cis and trans isomerization. So might be that kind of thing is operating in nature, but what we thought, can we just simply reduce it? If we reduce it, it will come closer, therefore we can just follow reductive elimination. Now if we have pyroclavin, festoclavin, we can just react with, Br plus or, 3,3-dimethyl allyl, reverse 3,3-dimethyl allyl pyrophosphate or corresponding bromide to give this kind of natural product. So what we thought, we had this intermediate, we had converted to this natural product, secoagroclavin, by simple reaction, with methyl lithium and then treating with citric acid, leading to this kind of tri-substituted double bond, and from their detosylation give us secoagroclavin. Now, when we try to do oxidation in secoagroclavin, we face a lot of trouble, which is understood later on that it is because of this nitrogen and this nitrogen, which can easily donate this electron pair to the oxidant, therefore it will oxidize to get nitron and all other species. Therefore, it was required to protect these two nitrogen with tosylate form, and then we followed selenium dioxide, and to our pleasure, we have seen that we can get a very nice yield of this mixture of compound, which was anyway reduced with borohydride to get this kind of alcohol. And then detosylation using sodium naphthalene gave us cyanoclavin 1 and cyanoclavin 1 aldehyde. Now, as per our hypothesis, we just reduce this double bond. Therefore, it can come closer to this nitrogen, forming iminium, enamine, reductive amination, give us fast total synthesis of prostaglandin and pyroclavin. Then cycloclavin, we thought that can we have another strategy for cycloclavin because it was isolated in 1969. First semi-synthesis came in 2008 from Woodward ketone. In 2011, first total synthesis, racemic total synthesis came by Peter Witt. In 2017, they make this partner as chiral. Therefore, they made first asymmetric synthesis of unnatural cycloclavin, not the natural one, because they had to follow a catalysis where, L-tertiary leucine they have used. But if you look at D-tertiary leucine, it is very, very costly. Therefore, they have shown only asymmetric synthesis of unnatural cycloclavin. So what we thought? We thought, can we have this kind of alpha-beta unsaturated ester? Now, we can again see two different things. It can follow ester aminolysis to give this kind of structure. It can also follow 5-endotrig cyclization, azamichael, to give this kind of structure. Now, if you look at endotrig, in this case, HOMO and LUMO not in proper alignment, and they are too far away to approach. However, in this particular case, we saw that this would be the preferred way, and in fact, what we have seen that we have made this kind of compound which is having extracyclic double bond. The interesting point was here, if you take this kind of compound, intramolecular head would give you this kind of explosive formation of vicinal stereogenic center through intramolecular head. That is where we have given the explanation why it should form exo bond, why not endo, because beta hydride is required. That is the syn beta hydride is the crucial criteria for this kind of reaction. So what we have seen that with this compound in hand, we have removed Bob group and then we have heated, and we saw only this compound, and there was no azamichael. And this we have further elaborated, isomerized, reduction, and removal of tosyl gave us this compound. Since in one step it is known, we have not shown this cyclopropanation. This is only one step known. So this gave us naturally occurring one. Now, since we followed enamine catalysis, we just changed D-proline to L-proline. That gave us unnatural one. So what I'm trying to tell here is that one strategy where we could make naturally occurring one by changing the catalyst structure or the ligand in the asymmetric state, we can make the other one. Therefore, I'm tracing is that asymmetric catalysis is very, very important. Now, if you look at lysergic acid and cycloclavin, now our question is this the intermediate where it is going towards this and going this? If we can do global reduction, that can go to cycloclavin. However, this kind of donor acceptor cyclopropane, if we just treat with Lewis acid, we just break this bond, and therefore you generate this dipole. Now, in absence of any nucleophile, it would just do a beta elimination leading to lysergic acid skeleton. Currently, since we have already made lysergic acid, we are just trying to couple with this partner to get ergopeptine and ergopeptine. Now, if you look at ergopeptine and ergopeptine alkaloid, nature is selectively oxidizing over here. Therefore, this oxygen is making OC bond, is nothing but sort of hemiketal type of structure. But in our laboratory, we are taking a counterintuitive approach, just reverse way. What nature is following, what we are saying is that since I have amino acid and lysergic acid, I can make carboxamide. Now this carboxamide can react with this ketone. It will form hemiaminal. That OH will react over there. Now once we reach there, from here to there, to here, go from here to there, we would just follow a reductive amination strategy. Why? Because if you look at here, nitrogen can push electron. Now you will see that this is ketone. Now, can I do imine reduction? Simple. Okay. So what we are proposing is that we can do 3-component reductive amination to go to ergopeptine. And if we just do 3-component reaction, that will be ergopeptine. By the way, there is no total synthesis in these alkaloids reported till date. And this partner can be synthesized from a diketopiperazine with the alpha-keto acid. Now come to this area. So this area, the interest came because of this kind of pyroindole input, and that is present everywhere, as I have shown. And now here, if you look at Larry O'Herman, the key player who actually showed the synthesis, in 1996, the first synthesis actually gave in 1996 O'Herman. Now, what we thought, can we have this kind of common intermediate to address this kind of natural product? Because if you look at, they are nothing but different topomers of each other, structural isomers. So towards this, to engage, deacylative annihilation grew our interest, and we have seen that they could do this process in asymmetric manner as well. Therefore, we started doing deacylative carbon-carbon bond formation, where we can see that it will go through a retroclasion activation to get this kind of in situ generated electrophile, which will react with palladium-02 to form carbon-carbon bond. And believe me, it is a very good process to get diverse structure. But we are mostly interested to get this kind of dimeric structure. Therefore, we made this kind of dimer, and we follow the sequential alliance to get this kind of meso as one of the major isomer. We have seen that changing base like sodium to potassium, this size also matters in deciding whether you need you need a C2 symmetry over meso or meso over C2 symmetry. So once we had this compound, we again followed the synthetic strategies, which are very simple, like you do oxidative cleavage, and then you do borohydride reduction, you do a mixonobu, reduce it, hydrogenate it, and then you get this kind of structural scaffold. Now through Redol, we got mesofolicanthine, now which was converted to mesochimonanthine, and as per the biomimetic proposal, what we did in this last step, we just rearranged this structure through this. Just took this H plus, it got this kind of protonated form, then iminium. Now this will be in equilibrium. Now it will hydrolyze to give this dialdehyde, rearrange itself, iminium stabilization, and just simply give us calicanthine. This is what I'm saying. The bio-inspired strategy is very important, because we know nature is making calicanthine from chimonanthine. Now, if you look at this kind of structure again, now this kind of structure, if you look at this particular things, is actually mesochimonanthine. Okay, now it is CO1, not C2. Meso can also do rearrange to get mesocalicanthine. Just now we have seen. But what about the chiral one? Towards this, Trost chemistry drew our attention. Trost shown that in 2005, they can make this kind of substrate in 97% of enhances selectivity. Then Brandstall showed that a sequential carbon-carbon bond formation can be realized in the presence of this kind of ligand. And they have shown a nice synthesis of cyanothalidine, which is having cytotoxic activity against human primary tumor cell, and reported in 2008. However, when it comes to vicinal or carbon power center, gives a lot of problem, which is reported by Shibasaki. They could get only 44% of these with very high enantiomer selectivity. They had to follow actually second diastereoselective Maiti. What we thought? Can we have this kind of structure? Look at this structure. This is plus, minus, and meso. Think about tartaric acid, two stereogenic center. Now, since it is asymmetrical, it can have a plus, minus as well as meso. Therefore, you will see three isomer: RR, SS, RS, SR. Now, can I charge with palladium 0 to get this kind of enolate? Now, stereogenic center gone. So basically, stereo mutation happen through a stereoablative process, where ablation of carbon dioxide taken place, and then allyl actually attach with palladium 0 to give this kind of enantiomer-rich compound. Now, if you look at this structure, now here we have allyl carbonate and ester. They would also follow the same thing to go there. So if you look at here, a dicat following a very complex mixture, okay? But if you take all this complex mixture, and if you find the right condition, which is shown over here, you will get only C2 symmetry over meso. And the DR was 17:1, 97% of enantiomer selectivity with this kind of ligands. So that in hand, we again did the simple synthetic manipulation, and we have seen that it can actually, this particular compound, if you do Redol, it gives this kind of structure, which is not a natural product, but could be future natural product. It's not isolated yet, but we can hypothesize it could be, because there are natural products, physovanillin of similar oxygen is known. This was characterized. Now with Mitsunobu followed by reduction, and Redol gave us polycanthine, which was also characterized. Right now, we are actually here. We are trying to expand this to get this intermediate, so that we can just do, cyclization over here. We do a Mitsunobu with azide and reductive cyclization over there to go there. Hopefully, we should be able to do that. Now, we have also planned for these, because this kind of compound we thought of having cyclization from there. Now, this can be synthesized from this aldehyde, which is nothing but allyl. Now, here is the interesting point. Look at this particular thing. This is not C2. This is a meso. So a meso unit attached. Now we are trying to do, asymmetric carbon-carbon bond formation into carbonite. Hopefully, we should be able to get it, this kind of intermediate, through this kind of proposed, enolate intermediate. That is under progress. But I would quickly like to show you some of the things, in this area. Okay, evident diterpenoid, the recent thing. The interesting thing is that the dimer of these, they are linked very nicely in the C and bond formation. Most interestingly, they can have in, thereby they are having actroselective, actrobisomer, digiamycin A, digiamycin B. There is one synthesis only by Baron of digiamycin B, no synthesis so far with this. There are synthesis digiamycin C by Ang Lee. So what we thought, can we got the idea of tyrosinase activity? If you look at tyrosinase activity, this drew our attention. 2005, Daniel Stack, Edward Solomon, Hodgson, and Hedman. What they have shown, the reactivity of natural tyrosinase, how melanin is getting biosynthesized. If you look at this paper, they have shown copper 1 can actually do oxidation of phenol to catechol, and that is what they have shown. In a control experiment, they have taken this substrate and they have got catechol, and catechol, of course, will give you orthoquinone. We thought of utilizing this idea to NN bond formation. So here is the literature. I don't want to go through my research literature here. It is published in 2016, how to make this monomer unit, not the dimer. What we thought, if we have N-center radical, can we do dimerization? That is what is hypothesized by Baron for the synthesis of digiamycin B. And in fact, if you have N-center radical, they are nothing but radical dance would lead to C-center, this center. Therefore, if you combine, that should lead to the digiamycin C. This is the simple hypothesis we have. If we have AB10, can we convert to this kind of structure through ipso substitution and followed by a catogen type of cyclization? So we just made this kind of synthesis, which is known, literature known. E.J. Corey has made this compound. With this, we have just coupled to get this, and then we followed cyclization. I'll complete in just 2 minutes, 3 minutes. Now, in ipso substitution, if you look at, if you have this kind of compound, it can do acylation. but if I have methoxy over here, it can do if so. So it's a very interesting thing actually. So from natural product to natural product. So with this in hypothesis, what we did, this particular bromo compound we converted to nitro. And this nitro and bromo we did Suzuki, then we did Cadogen to get this cycle. So basically in 4-5 steps, we can get the core structure of this. And from there we could synthesize GMIC A by simply, oxidation of this primary hydroxyl group over secondary. We can also do similar process where we can make ester. This is also natural product. So this is where the most interesting thing. When we took this as a model substrate, we use copper I, N-methyl imidazole, and oxygen. The way tyrosinase is doing the thing. Okay, we could generate radical, and in practice we have seen that we could synthesize this kind of scaffold. Not good yield, but not bad. Baron had shown 28% yield of digiamycin B. But what we can see that in one pot, we can synthesize both of them. Baron said digiamycin A is not stable, that may be rearranged to B. Therefore, it is only digiamycin B which is done by Baron. But we could actually synthesize both of them. Not only that, if we change this condition to copper I, this should be phenanthrone. I'm sorry. By changing this ligand, we have seen that we can actually make this kind of curve CN1 formation in 46%. So these are the model substrate. Hopefully, in the next 1 month or so, we should be able to make the right substrate. In the right substrate, we need one hydroxyl group over here. This is a model. Okay, so there are other things. I don't want to go through this silazondorphone and other thing. And we are also working benzoserine. I don't want to go through it. So I would like to conclude. So what I'm trying to tell you is that natural product and analogs are very important. We need to devise strategies. Bio-inspired strategies will be very good because it will avoid protection, deprotection. Asymmetric catalysis is very important in order to make the scaffold. With this, I would like to thank again everyone, all these funding agencies, particularly directors of ISR Gopal, ISR Kolkata, all of my PhD students, current PhD student, of course, you guys for your, all questions for listening. I'll be happy to address if you have a question. Thank you.
Thanks, Professor Bisoi, for your illuminating lecture. And now you have seen last 45 minutes that how the heterocycles are synthesized, and not only that, how so many chiral centers are installed in that particular positions. So now the talk is open for discussion. Do you have any queries?
Okay, I have a question, Dilip. So can I have
Please go ahead.
Okay, so on the part that, in the lysergic acid synthesis, that when you are trying to do this, Michael addition reaction, and you said there will be kind of steric, electronic, and something stereoelectronic control. So that particular slides, I have some kind of, here it is. So in that oxygen, that where you are showing that depending upon the R group and the steric and playing an important role. But that if R group is the large and whatever it is, because it's away from this center, so how it is playing the steric effect there, so that I cannot follow. Can you please elaborate a little bit?
Yeah, so it's a very nice question because it is obvious question, by the way, because the question is that if you have R group, whether it is small or big, how it could actually influence this outcome.
Yes.
The question Professor Mal is asking, because this oxygen is actually sp3 hybridized. Therefore, you have two lone pair as well as one bond pair. So they can actually, do bond pair, lone pair, this exchange. So what we have seen, if you couple with this bulkiness as well as this stereogenic sector, we have seen that this kind of substrate like tertiary butyl could not give any product. We could just isolate this starting material. I mean, approximately 60% starting material we could isolate, and some of the decomposition is there. So this bulkiness, we feel is that it is because of quiniquidine. Quiniquidine is already having, this kind of bicyclostructure. We have to do actually, this is giving me a hint that we should do a DFT or something with the theory, and then come up with some kind of approach, because this hydrogen bonding, all these things showing is all hypothetical, because we really do not know what is the length in an angstrom. Okay, so therefore we need to do some kind of calculation. But what we believe is that E, along with bulkiness, is the factor. That is why we mention sterics.
Okay, good one. So another one, just small queries about that. So that is your ergopeptin synthesis where you showed the hemiketal. So I think it is a kind of hemiaminal, rather you can call, because that should be, here it is. So this particular center, the stereogenic center, the hemiaminal type of derivative, which is expected to be much more unstable. But how come you're getting the stability over here? Which is driving factor?
Yeah, very nice. This is the question we also ask. If these natural products are isolated and these are stable, there are at least 20 alkaloids in ergopectin by changing this R group as well as in diketopiperogen. There are more than 20 alkaloids also in this skeleton. You can just simply think that nature can generate this kind of diketopiperogen from any amino acids. Okay. Now the question is, if this kind of structures are stable and they have been isolated, we ask a question that you are perfectly correct. I said hemiketal, but they are not hemiketal. If you look at this position, this is nothing but carboxamide. However, if I take these functionalities, this is not carboxamide now. Because of another carbonyl group, this nitrogen lone pair is not only stabilized by this side, it is not stabilizing only this side, but also this side. Therefore, it is a type of imide, like succinamide. It's not carboxamide, succinamide, or other imide type of functionality. Now, if you look at the imide type of functionality, reduction of imide is very easy. Then carboxamide. Okay, so what we think is that it is because of this imide type of functionalities. If you consider these two carbonyl, okay, since they both are pulling electron, get stabilized. What we believe is that leads to the stability of this kind of compound. And what we think is that if this is the case, can we just simply think in layman's language, layman's way, that it is just a carbonyl. I take this carboxamide and take this compound, and I just use Dinstark and just remove, I just heat it. It will form hemiaminal. This hemiaminal will form this 4C bond.
Okay, all right. Thanks, Alokas. Okay, we can discuss later also here because more time is there.
Sure.
Any more question? Okay, Professor Viswa, I have a general question.
Yes.
Like, very difficult job I found to synthesize all these natural product or alkaloids.
Yeah.
To install the chirality. So, do you take any modeling type of DFT calculation or like that to use different type of chiral auxiliary to introduce chirality? So how do you do all those type of solve this type of problem?
Yeah. So it's a very nice question. Very, very nice question. Thanks, Dilip. That's a very, very nice question, particularly for student. This question I would expect from student. See, look at the structure. No synthesis is reported for this natural product, by the way. These are the dimer of a tri-terpene. No synthesis is reported in that. But since we are working in this area, hopefully we should be able to complete it. Now the question is how we think, how we do a retrosynthesis, and how we come up with a particular asymmetric strategies. Now, as Professor Maiti correctly said that you can also follow a chiral auxiliary approach, Or you can also follow a catalytic asymmetry approach, which is actually done by nature, not the chiral auxiliary approach. Now look at this molecule. So how we think? We try to find out the first thing is that symmetry. If you look at this molecule, they are nothing but dimer by looking at this. Okay, because what I can see that these are actually two trimeric things. If I can install chirality in one of the monomer, I can able to just couple them so that if the complexity comes. Now, if you look at this structure, we try to find out unified strategy. By looking at this literature, we could see that these are the all natural product isolated. Okay, no asymmetric synthesis is known in there. In order to do that, we have to follow some kind of poly type sequence. Now, we can do actually chiral auxiliary approach, but the problem with auxiliary is if you look at the marketed chemicals, one of the isomer will be very cheaply available, whereas other one will be very costly, except tartaric acid and other. Okay, therefore we think that if we can control that construction of chirality through catalytic way by changing this other enantiomer of the catalyst, we should able to approach to the other antipode of the natural product. Okay, now while doing so, initially we go through the literature and then we found out that catalysis, which catalysis we should do to get that particular pore. Okay, but you have given a very nice idea that we should able to collaborate with theoretician to find out what kind of transition studies actually playing. Like what Professor Mal has asked, very genuine question, that how this particularly sterics, what we are hypothesizing, is really controlling the reactivity. So to know that, we need to do some kind of collaboration with the theoretical people. So at ISR Kolkata, we are actually looking collaboration with Professor Devashish Kole to find out some of this kind of transitions. Okay, but again, we do not follow chiral auxiliary approach simply because one of the enantiomer of this chiral auxiliary will be available, very cheaply available. I mean, cost-wise, but if you look at the other antipode, will be very, very costly. So only one way to approach is asymmetric catalysis.
Yeah, basically you are starting with the chiral molecules. You are not actually creating a chiral center in any way.
We are not starting with chiral.
So the question is,
chiral.
I think that will answer to the question of Dilip actually. That's what he was asking, whether how did you control it. Since you are starting with the chiral molecules, you can have a control over there actually. Yes.
We are not, by the way, excuse me. We are not starting with a chiral molecule. We are starting with a flat molecule. In one particular first step, we are generating chiral.
Where are you standing? Which step you are talking?
Any synthesis if you take, like in this particular synthesis, we start from a flat molecule, we generate a chirality, therefore it should trigger the cyclitis. We are not starting with chiral molecule. We are starting with flat molecule. Let's start there. We are starting with a racemic and plus minus and meso. This is chiral but non-racemic, racemic molecule. We are generating enantio enriched through asymmetric catalysis. I've got it. We are starting with flat molecule here. We are starting with flat molecule. We are generating chirality through this. Therefore, we have the flexibility.
And this is fine. This is okay.
Yeah.
But the first question which you showed the big, dimer, but there actually you are starting with the chiral molecules, correct?
Yeah. Because that is what is.
Yeah, that's fine. That was the question.
Yeah.
Thank you.
Okay, so time is up. We should thank Professor Bisoi for his nice talk and nice work.
Thank you once again. for the kind invitation and for this award. Thank you, Professor Maiti, and thank you, Professor Bhatt. Thank you very much.
Am I audible? Am I audible? No.
Yes.
Am I audible? No.
Yes, sir, we all can hear you.
Some others
No, I think for one person there are two devices on. That's why this is echo problem is coming up. So please check whose two devices are on.
Now, sir, आपका, you have two devices on. Professor Sunil Tolapatra has two devices on.
Okay. But he's not.
Yeah.
Okay, all right.
So thank you, Dilip, sir. Thank you, Professor Dilip Kumar Maiti, sir, for chairing this session. And also thank you, Alokes, sir, for your lecture. Now I would like to request the chairperson of this session and the president of CRS to felicitate Professor Alokesh Bishoy. Project Gopal, sir.
Yes.
I wanted.
অলোকেশ বাবু, আপনাকে প্রেজেন্টেশনটা বন্ধ করতে হবে। Yes.
Yeah, I have removed.
Okay, thank you. Thank you very much. Excellent presentation.
Thank you.
So, is it visible now?
Yes, sir.
Okay, so thank you very much, Professor Alokesh Bishoy. So, based upon your academic achievements, and well, the society has decided to honor you by the offer of this silver medal and a memento and a certificate, as it is. So, thank you very much, Professor Bishoy, and I hope you accept it. And I congratulate you as a president of this society.
Thank you very much. It's a great pleasure to accept. Thank you, Professor Bhatt.
Thank you very much. And thank you, Professor Dilip Maiti, for chairing the session. Thank you.
Thank you.
Thank you, sir. Now,
Thank you, Dilip.
Thank you. Thank you.
So now we will move to our next lecture. Sunil sir, kindly. Thank you, sir. So our next hour lecture is by Dr. Mayuri Napakoda from the University of Ruhuna, Yale, Sri Lanka. Professor P. Jaisankar from CSIR IICB Kolkata will be the chairperson, while Dr. Mayuri Napakoda will deliver his hour lecture. I'd like to request Professor P. Jaisankar to kindly take over from here.
Thank you. Thank you very much, Dr. Tanmoyee Bhattcharjee. And at the outset, I would like to thank Professor Gopal Bhatt, the president of the society, Chirantin RASAYAN Sanstha, and the organizer of this RASAYAN 9, and the co-organizer of this conference, the Midnapore City College principal, and all the office bearers of the society, and all the participants. It's really my pleasure to be part of this conference, and this is the second time, in fact, this year. And thanks to Braja for the fantastic, opportunity and the affection. And I'm really honored to be here. And in fact, there are a lot of seniors, and Professor Talapatra, Professor Ray, and my friend Professor Maiti, and Professor Prasijit Mal, and there are many other, luminaries in the chemistry field, and I'm so lucky to be part of this. And we are also so lucky to have fantastic speaker of this session, Professor Mayuri Taranga Napagoda. I'm sorry, Dr. Mayuri Taranga Napagoda. And she is the recipient of the second award lecture And it's my pleasure to give a small introduction about her and about her achievement. Dr. Nappakoda has completed her PhD in Natural Product Chemistry from Friedrich Schiller University, Jena, Germany in September 2014. And earlier she obtained her Master's of Philosophy in Chemical Sciences and postgraduate certificate course in Advanced Organic Chemistry from University of Prithidipa, Sri Lanka. And she has completed her graduation in chemistry as well as the bachelor's degree in botany with the first class honors from the University of Colombo. So before that, after completing her PhD, and Dr. Nappakoda has joined the teaching, the department of the University of Colombo, as in the plant science department, starting from as a teaching assistant way back in 2002, and then became lecturer, joined as a lecturer in the biochemistry in the Faculty of Medicine, University of Runa, Sri Lanka. And she also served as the head of the Department of Biochemistry from 2016 to 18. And at present, she is the senior lecturer in biochemistry since 2010 to date. And Dr. Nappakoda has achieved a rare opportunity, many more awards she has received, to say few. And she has received International Max Planck Research Schools Fellowship in Germany from 2010 to 2013. And she is also recipient of another prestigious fellowship, DAD Fellowship, German Academic Exchange Fellowship like AVH, Alexander von Humboldt, Professor Braja has received. So it is also one of the prestigious fellowship in Germany, and she is the recipient of that. We are so happy about that. And she has received Max Planck Travel Stipendium to attend the conference Max Planck symposium, series of symposium in 2018, 19, 17. And she is also recipient of the Best Poster Award, presentations, in many conferences, and many, wherever she attended, she secured the award, and it's really fantastic. She must be a good orator and good presenter also. And Dr. Nappakoda has published many publications to her credit. To say few, she published in Molecules, Journal of Ethnopharmacology, and the European Journal of Integrative Medicine, and there are many more actually, like BMC, Complementary Alternative Medicine, and of course Journal of Molecular Nanotechnology, Nanomedicine, etc. And she has also written book chapters. She has edited the book chapter volumes, about 4, and she has written full book, 1 full book and 4 full book chapters. And as I told you that she is serving in many editorial and examiners in the editorial board of the many journals, and she is at present guiding PhD students and master's degree and undergraduate students in the University of Runa. With a small introduction, I would be happy, and it's my pleasure to invite Dr. Mayuri Taranga Nappakoda to deliver a lecture. Dr. Nappakoda, thank you.
Okay, thank you very much, sir, for your kind introduction. I think all of you can hear me. Is it clear?
Yes,
okay.
Yes.
Okay. So, good morning, everybody. And first of all, I would like to extend my sincere gratitude to Professor Bag and his team at CRS for giving me this opportunity to deliver this award lecture. Okay, so I will move on to my lecture now. I think all of you can see the slides.
No, not yet.
Okay.
Not yet.
Yeah, just a minute.
Yeah.
Dr. Nappakoda, can you just briefly?
Can you see it now?
Yeah, it's fine. It's fine. Yeah, it's fine. Thank you.
Okay. Thank you very much again. So it's a great pleasure for me to meet you all today, and I hope my lecture would be some more informative for young and budding scientists, especially budding chemists and biologists who are intending to undertake a career in the field of chemistry. So the title of my lecture is In Vitro Enzyme Inhibitory Assays, an indispensable tool to identify bioactive metabolites for drug discovery. So this is the outline of my lecture. So in this lecture, I would briefly give some information about these topics. First one is plants as a source of medicine. Then from plants to the pharmacy shelf, drug development process in brief. Then the enzyme inhibitory assays for the selection of bioactive metabolites. Here I am going to focus mainly on the enzyme inhibitory assays that have been used to identify the anti-inflammatory metabolites from plant extracts, and also for the formulation of skincare agents. So let me start my lecture with a topic about the plants as a source of medicine. As you all know, medicinal plants form the basis of various traditional and folk medicine that have been practicing for thousands of years. Even today, plants are considered as rich source of therapeutic agents for the treatment and prevention of diseases. According to the World Health Organization, WHO, about 80% of the inhabitants in the world depend mainly on traditional medicine for their primary healthcare needs. And at present, it is estimated that more than 35,000 plant species are employed for medicinal purposes. And up to 50% of the approved drugs during the last 30 years are from either directly or indirectly from natural products. For example, in the area of cancer, out of the approved 175 small molecules over the time frame from 1940s to 2014, 85, that means 49% were either natural products or natural product derivatives. And most of you are aware that the modern medicinal plant research started with the discovery of the alkaloid morphine. And since then, many bioactive secondary metabolites have been discovered. These are few examples. The salicin and its derivatives isolated from Salix alba or white willow. Then the cardiac glycoside digitoxin isolated from digitalis plant. Then the antimalarial drug quinine from cinchona, and the very famous vinblastine and vincristine, which are used as anti-cancer agents from the Catharanthus roseus.
Is it possible to mute remotely Professor Talapatra's mic by any means, microphone?
Yes, I think now it is now it will be audible. I had one mistake.
Yeah. Fine, sir.
No, I had
now
two,
you are.
I had two screens side by side. That is why it was.
Ma'am, you can continue. Please continue.
Okay. Yeah. Thank you. So not only the isolated compounds, even plant extracts itself are also commercially available over the counters, especially in Western countries. For example, the St. John's wort, the Hypericum perforatum extract is available as antidepressant drug, and the extracts from the leaves of ginkgo biloba is used to improve memory, and these drugs are also available over the counter, especially in Western countries. However, the journey from plant to the final drug is not very easy process. Okay, it's a very, very long journey. So it is a very complex, time-consuming, and expensive process that is carried out in mainly 3 elaborate steps. So I would like to give you some idea about the various steps involved in drug discovery process in the next few slides. So as I said earlier, the development of new drugs from medicinal plants is a complex, time-consuming, and expensive process. It involves 3 major stages: pre-drug stage, quasi-drug stage, and full drug stage. And the first stage of drug development is the pre-drug stage. This involves the information-driven selection of plants, mainly based on the indigenous use, or it could be from the results obtained from a previous animal study. So we can select the suitable plants for this process. And then in the quasi-drug stage, the extracts are prepared, the phytochemicals are screened, and the structure and the compositions are evaluated. And also the bioactivity evaluations are carried out for the identification of possible lead compounds. And if necessary, the lead compounds are subjected to structural modifications as well. Then the preclinical studies are conducted using animal models. And then in the full drug stage, the clinical trials are carried out at different phases, and the approval and the registration is obtained to enter this as a marketed drug. As I mentioned earlier, the new drug candidate must undergo preclinical trials followed by different stages of clinical trials. These clinical trials are named as phase 0, which is optional, then phase 1, phase 2, phase 3, and the experiments. These animal experiments are in vivo experiments. And during these experiments, different doses of the particular drug is used to determine the pharmacodynamic, pharmacokinetic, and toxicology evaluations. Now we will look at different stages of clinical trials. Okay, the phase 0 experiments, they are optional. So these are carried out with a small group of individuals, usually 10 to 15, and a single subtherapeutic dose is given to these individuals to gather pharmacokinetic information. And these studies would enable to assess whether the drug candidate performs as expected to take forward into the further development in the next stages. In phase 1 stage, the new drug is administered to 20 to 100 normal healthy individuals, and it is to determine the maximum tolerated dose of that particular drug, and also the common and serious adverse effects associated with that drug. the pharmacological, pharmacodynamic, and pharmacokinetic properties are also evaluated by these studies. Then in the phase 2 studies, okay, these studies are conducted with several hundreds of patients with specific disease. Okay, so in phase 1 stage, the healthy individuals are used, but in phase 2 studies, the patients with that particular specific disease have been recruited. Okay, and the study population is well defined by inclusion and exclusion criteria, and based on the dose or dose range determined in the phase 1, the dose response in patients and the drug's biological activity and efficacy are evaluated. Okay. About 1/3 of tested new drugs move on to phase 3 trials from phase 2 stage, and these phase 3 studies are carried out using a large number of patients and with specific disease. And this phase of study enable to determine the efficacy, effectiveness, and long-term side effects of the drug. Usually about 25 to 35% of the new drug candidates from phase 3 progress to the next stage, that is phase 4. And these phase 4 trials are long-term studies involving more than 10,000 individuals of the relevant patient population. And these studies are normally carried out after obtaining the approval from the regulatory agencies. And this study aims to assess the drug's real-world effectiveness. And in some instances, the outcome of this phase 4 studies would lead to a withdrawal of the drug from the market, or it could lead to restrict that particular drug to a particular use only. And this slide shows roughly the time taken for the development of a new drug. So you can see the basic research, okay, starting from the basic research, and when it comes to the phase 4, okay, it takes usually 15 years. Okay, so it is a very complex and a tedious process. In the drug development process, the success is mainly depend on choosing the right bioassay or test system for the identification of lead compounds. So choosing the right bioassay or the test system is very, very important in drug development process. Okay, so these bioassay tests should be simple, quick, and relevant, because there are a large number of compounds or samples are there to be screened at the beginning. Okay, and human testing is not possible at early stage, so all these testing should be done in vitro first, and these in vitro tests are usually cheap, and they are easy to carry out, and they are less controversial, and even today they can be automated. Then the in vivo tests are required to choose the drug interaction with specific target. Okay, or these evaluations are carried out, and also this in vivo test would monitor the pharmacokinetic properties of a particular drug. Now let's look at in vitro test. Okay, so these in vitro tests do not involve live animals. Instead, specific tissues, cells, or enzymes are used. And enzyme inhibitors can be tested on pure enzyme in solution. So it is quite easy to carry out enzyme inhibitory assays using isolated pure enzymes. And in addition, the receptor agonist and antagonistics can be tested on isolated tissues or cells. And also antibacterial drugs can be tested in vitro by measuring how effectively they can inhibit or kill the bacterial cells in culture. So here you can see an ELISA plate where we have evaluated the efficacy or inhibitory action of a particular enzyme. Okay, and we can test large number of samples at a time. 96 samples we can test in a single shot. Okay, so it is very easy to carry out if the conditions are optimized. And then in the case of in vivo assays, these tests are performed on animals on which the clinical condition is induced to produce observable symptoms. Okay. Then these treated animals are again treated with a particular drug candidate, and then check whether the drug alleviate the problem by eliminating the observable symptoms. For example, in the case of developing the non-steroidal anti-inflammatory drugs, okay, the inflammation was induced on test animals. So with this basic introduction to the drug development process, now I move on to the enzyme inhibitory assays that have been used in the identification of bioactive metabolites. Before going to detail, let me give a brief introduction about the enzymes. As you all know, enzymes are usually protein molecules, okay, and they act as biological catalysts of various metabolic pathways required for the viability of the cell. And if you take one human cell, it may contain hundreds or thousands of enzymes. What is interesting in drug development is that these enzymes can be used as drug targets. This is mainly because of their roles in specific chemical reactions of pathogenic relevance, as well as their susceptibility to inhibition by pharmacologically tractable small molecules. And usually these enzyme inhibitors are low molecular weight chemical compounds, either natural or synthetic in origin. And these inhibitory compounds can either reduce or completely inhibit the enzyme catalyzed reaction. A selective inhibitor could block either a single enzyme or a group of enzymes, leading to the disruption of a metabolic pathway. When we talk about the potency of a particular enzyme inhibitor, we often use the term IC50. IC50 stands for half maximal inhibitory concentration, and it is a measure of the potency of a substance in inhibiting a specific enzymatic reaction. And this can be determined by plotting the dose response curve as shown in these two diagrams. Now we will discuss about the role of enzyme inhibitory assays in the search of anti-inflammatory remedies. Okay. First of all, let's understand the term inflammation. Inflammation is a part of complex biological response of tissues to harmful stimuli such as pathogens, irritants, or other chemical agents. Okay. So this inflammation is usually characterized by 5 symptoms: heat, redness, swelling, pain, and loss of function. Although acute inflammation is normally considered as a beneficial thing, the uncontrolled and chronic inflammation is detrimental, and it can be related or it can lead to various pathological conditions. When we talk about inflammation, we cannot forget about eicosanoids. Okay? Eicosanoids, these are crucial signaling lipid mediators derived from the metabolism of arachidonic acid. And it includes prostaglandins, leukotrienes, and lipoxins. And these eicosanoids function in diverse physiological systems and pathological processes such as mounting or inhibiting inflammation and other immune responses, then contributing to the perception of pain, regulating cell growth, controlling blood pressure, okay, such like that. These eicosanoids are involved in many physiological functions. And the suppression of the biosynthesis of eicosanoids is important therapeutic approach in the management of inflammatory conditions. Here you can see the inflammatory cascade. If I brief you some important points here, due to an injury or an infection or another inflammatory stimulus, the cell membrane phospholipids, they undergo hydrolysis in the presence of the enzyme phospholipase A2. Then the arachidonic acid is released, and this arachidonic acid can be either directed towards the formation of leukotrienes or lipoxins. And this enzyme 5-lipoxygenase is involved in the conversion of arachidonic acid into leukotrienes and lipoxins. On the other hand, this arachidonic acid, the released arachidonic acid from the hydrolysis of cell membrane phospholipids, okay, it can be directed towards the synthesis of prostaglandins. For this process, the enzyme cyclooxygenase is involved. And the commonly used anti-inflammatory agents like steroidal drugs, they would inhibit the phospholipase A2 action, and the aspirin and endomethacin, these drugs would inhibit the enzyme cyclooxygenase. However, these steroidal and non-steroidal anti-inflammatory agents are reported with severe adverse effects. Therefore, there is a necessity to search for novel anti-inflammatory agents, especially from nature. And if we look at leukotrienes, okay, these leukotrienes, they contribute to various inflammatory and allergic reactions in the pathology of conditions like asthma, allergic rhinitis, atherosclerosis, cancer, etc. And as I mentioned in the previous slide, this 5-lipoxygenase or 5-LO enzyme, it catalyzes the first two key steps in leukotriene biosynthesis. And then the PGE2, prostaglandin E2, which is formed from the arachidonic acid under inflammatory conditions by the action of cyclooxygenase 2 and then by the action of microsomal prostaglandin E2 synthase 1 enzyme. So the current research revealed that the dual interference with MPGS1, microsomal prostaglandin E2 synthase 1, and 5-lipoxygenase would be more efficient to reduce inflammatory deregulation. Here are some well-known 5-LO and MPGS1 inhibitors. This one, Boswellia serrata. This plant is very well-known example of anti-inflammatory agent, and this extract is available in the markets in Western countries, and the active ingredient in this extract is found as different types of boswellic acid. And another example of plant extract that is commercially available as anti-inflammatory agent is Hypericum perforatum extract. I earlier mentioned about this plant because this extract is used as an antidepressant agent. Not only that, this extract shows potent anti-inflammatory activity as well. The active ingredient responsible.
Excuse me, Professor Napagoda. I think we have to go a bit faster as we are running out of time actually. Eh?
Okay. Yes.
Sorry to interrupt you.
Thank you. Yeah. Okay.
Thank you.
Okay. So this active ingredient in this extract is hyperforin. And there are some other plant species and phytochemicals reported with 5-LO and MPGS1 inhibitory potentials that include cannabis, nettle, Davis claw, and the phytochemicals include curcumin, then epigallocatechin gallate, carnosol, carnosoic acid, etc. Now let's move on to the anti-inflammatory activity of Sri Lankan medicinal plants. Although several research groups in Sri Lanka have studied the anti-inflammatory activity of Sri Lankan medicinal plants. These assays were, almost all of these assays were based on classical in vivo models, including that core edema model. And these in vivo models are inappropriate to reveal the underlying mechanisms of action. Therefore, we have undertaken a research project to evaluate the anti-inflammatory activity of Sri Lankan medicinal plants using in vitro inhibitory assays, and also to study the phytochemical composition of these extracts to identify the inhibitory mechanism of these potential plant extracts. One example of the plants we have studied is Plectranthus silenicus, and the active ingredient in this plant was found responsible for the anti-inflammatory activity is tentatively identified as Coleon P by LCMS analysis. And here you can see the hexane and the dichloromethane extract have inhibited the enzyme 5-lipoxygenase with these IC50 values. The second plant we studied is Munroria pinnata. And here the DCM extract was found to be a dual inhibitor of 5-LO and MPGS1 enzyme. And you can see the IC50 values here. And the GCMS analysis indicated the presence of phytosterols, fatty acids, sesquiterpenes, acyclic diterpenes in this active extract. And also we have found that this extract contains the compounds like beta caryophyllene, then caryophyllene oxide, alpha tocopherol, beta cystesterol, amyrenes, which have already been reported with anti-inflammatory activities. The plant Leucas silinica also found to be a dual inhibitor of 5-LO and MPGS1, and the phytochemical analysis again revealed the presence of various fatty acids, sesquiterpenes, phytosterols, etc. In a more recent study, we evaluated the 5-LO and MPGS1 inhibition of 28 plant extracts prepared from 7 plants, and different extracts prepared from these 7 plants shows different degree of anti-inflammatory activities by inhibiting 5-LOO MPGS1 enzymes. The active plant extracts were found from Garcinia cambogia, Hibiscus furcatus, Mollugo cerviana, Ophiurosa mungos, and Porto scandens. And here you can see the IC50 values for 5-LO and 5-LO inhibition in both the cell-free assay, where we use the recombinant free enzyme, and in the cell-based assay, we have used nucleophiles. And the MPGES1 enzyme inhibition was determined using the pure isolated pure enzyme. And we have identified garcinol in Garcinia cambogia as the active ingredient for the anti-inflammatory activity of Garcinia cambogia plant extracts. Based on the literature, the 5-LO inhibitory potencies of well-recognized anti-inflammatory medicinal plant extracts were found to be having 20 to 80 microgram per milliliter the IC50 values, and even the extracts of gum resin of Boswellia serrata, one of the popular anti-inflammatory remedies in Western countries, is found to have IC50 values in the range of 8.4 to 30 microgram per milliliter. So in comparison to the 5-LO inhibitory potential of the plant extracts reported in literature, the 5-LO inhibitory potential in Sri Lankan medicinal plants is found to be remarkable. And the ethyl acetate extract of Pothos candens repress the activity of MPGS1 with IC50 value of 0.1 microgram per milliliter, and such a high potency of IC50 value has not been yet reported in any medicinal plant. And even the synthetic inhibitor used as positive control was found not to be superior over to our extracts. So we can conclude that the extracts prepared from Sri Lankan plants possess high pharmacological potential.
Dr. Mayuri, you have got 5 minutes time.
Yeah, I will complete. Yeah, thank you.
Yeah, that's fine. Thank you.
Then I will quickly move on to another assay, enzyme inhibitory assay we have used to evaluate the anti-inflammatory potential. That is the inhibition of xanthine oxidase. So the xanthine oxidase catalyzes the last two steps in purine degradation, where hypoxanthine is converted into xanthine and then into uric acid. This uric acid is the final product of the catabolism of purine nucleotides, and it has a limited solubility in plasma, so the excess can get crystallized in joints. So the accumulation of uric acid in joints, tendons, and surrounding tissues leads to inflammation and the condition known as gout. So the xanthine oxidase inhibitors are used in medicine. This includes allopurinol and febuxostat, and these are reported with various adverse effects. Therefore, there's a need to search for novel xanthine oxidase inhibitors with high therapeutic potency and a lesser side effects. But no studies on xanthine oxidase inhibitory potential in medicinal plants were carried out in Sri Lanka until we have undertaken this study. And we have found that the dichloromethane extract of Leucas salonica possesses a potent xanthine oxidase inhibitory action. And this is the first time that Sri Lankan plant species was reported as a potential source of natural xanthine oxidase inhibitor. Then I will quickly mention about the enzyme inhibitory assays in the search of skincare agents. Under that, we can consider the skin whitening potential, where we mainly focus on the tyrosinase inhibition. Then the anti-aging potential can be evaluated using the enzyme inhibition of hyaluronidase, elastase, and collagenase. Professor Bizai has mentioned about the tyrosinase enzyme. So this enzyme is involved in the melanogenesis pathway, and it is the key enzyme involved in this process, and it is targeted in skin whitening agents. So we have evaluated the skin whitening potential in different plant species, and we have found a strong inhibition of the tyrosinase enzyme by the extracts prepared from Cassia auriculata. And we have, at the moment, we have prepared a formulation, skincare cream, using this plant extract. And with these things, I would like to conclude my talk, and the take-home message of this lecture is that the in vitro enzyme inhibitory assays are important for the initial bioactivity screening of crude plant extracts, for hit identification, and for the validation and characterization of the mechanism of action of the lead compound. Before I conclude, I would like to acknowledge the funding agencies, my research students, and thank you very much for all of your kind attention. Thank you.
Thank you, Dr. Mayuri. Napakoda, I'm sorry that I have disturbed you in between a couple of times, but I think we are running out of time. That's why.
It's
So,
okay.
excellent presentation. Thank you so much for wonderful presentation. Actually, how beautifully you have explained, starting from the plants as a source for the medicine. You know that it's true that more than 50%, almost 50% of all the existing drugs are based on the plants. And nicely explained about the stages of the drug development as a whole, especially the medicinal plants-based drug actually. And you came to the point where you beautifully explained that you could identify the 5-LO and inhibitors and xanthine oxidase inhibitors and tyrosinase inhibitors from the medicinal plants actually. So thank you very much and keep doing this wonderful work actually. I have only one question before I invite the audience to ask question actually. Is it the same species which you said about Lucas, I think Xylonica, which is different from the, are you aware that we are also having a fantastic species, I think Lucas aspera? Have you heard about Lucas aspera?
Yeah, it's a different species. This Lucas Xylonica is the Xylonica means it is found mainly in Sri Lanka. Xylonica comes from Sri Lanka.
Okay.
So did you confined to Sri Lanka?
Oh, I will go through that actually. Is there, how many similarities are there in phytochemicals wise actually? I mean with aspera actually, which is very widely used in India actually. It's one of the fantastic one actually. We use in South India, we use it for shipping and all those things. Anyway, so I just check the similarity. That's fantastic work. And with this, I would invite the audience to raise the questions. Yes, Dr. Biplab Maiti.
Yes, sir. Good morning, sir. I am the student of Midnapore City College.
MSc second. Please go ahead.
I have a question. Can I ask to Professor Dr. Maudi, ma'am?
Yeah, sure.
Okay. Thank you, ma'am. Actually, I want to know. I know that IC50 value is all about inhibitory concentration, and it is a specially biological function of a plant base. But I want to know how it is measured after prepare a drug, or when we going to prepare a drug, it is a considerable thing. Why it is a considerable thing to a natural plant?
Yeah, because this IC50 to determine the IC50 value, we have to do a dose response study. That means we have to use different doses of that particular drug, okay, or the extract. Okay, then we have to determine the percentage of inhibition or the remaining activity of the enzyme. Okay, then we can draw the graph. Okay, if I can go for the slide, then it would be easy for me to explain. Just
Yeah.
This one. Okay. So we can use different concentrations, different doses, and then we can determine the activity at these different doses. Okay. Either we can determine the remaining activity of the enzyme or the percentage inhibition, and then we can plot this. So we can, using this plot, we can determine the IC50 value, the 50% inhibitory concentration. And if we have this IC50 value, we can compare it with the other possible drug targets or the reference drug, so that we can get an idea about the potency of that particular substance.
Okay.
Is it clear?
Okay, ma'am. Okay, yes, ma'am. Actually, ma'am, is it mentioned? It is monitoring according to any physically instrument or any other some software basis, that is, I know that molecular docking, just like that, or it is any instrument that we measure the IC50 value?
Actually, to plot this graph, we normally use these statistical packages. Okay. Using any statistical package, we can draw it, draw the curve, and then determine the IC50 value.
Yeah. But the question what is asking that which instrument is used for drawing
Yes,
this, getting the information. Actually, probably you have to use the spectroscopic technique actually to measure the light intensity, because these are all, say for example 5LO is based on the on the soybean, and when you use the inhibitor, the color of the solution will be from the rose or kind of violet to colorless, correct? The color will fade actually.
Yes.
So the light intensity is measured colorimetrically, and then versus the concentration is plotted actually.
Yes.
That's like a spectroscopy measurement, I think.
Yeah, depending on the type of the enzyme assay, either we can use the spectrophotometer or any other instrument. That depends mainly on the type of the enzyme inhibitory assay.
Correct.
Thank you, ma'am. Thank you.
Jaisankar,
You're welcome.
Dr. Jaisankar, am I audible?
Yes.
Am I audible?
Yes, sir. Please,
Yes.
sir. Please.
I have only a simple comment as an information that the drug discovery process that has been included in our book. Just a moment. In our book that has been published. Oh my God, where is it? In our book that was published several years back, the Chemistry of Plant Natural Products, and chapter 33. There, whatever she has given, this Napagoda has discussed very nicely, and so there in the drug discovery process we have mentioned about the pharmacodynamic and pharmacokinetic properties and some toxicological terms. All these things people don't know, so it has been included in the second volume of Chemistry of Plant Natural Products, published by Springer in 2015. I don't know whether Jaisankar has seen that, but if you see, there is a natural product chemistry as well as stereochemistry, one chapter in detail.
That's fantastic, sir.
And we are now in the process of writing another book on, not another book, a monograph on stereochemistry itself, as invited by Springer, and now they call it Springer Nature, and that will be published maybe a few months later.
Very nice, sir. Thank you so much, sir. Thank you so
Thank
much for this information.
You will be able to procure these books and see it, Dr. Jaisankar as well as Dr. Napagoda.
Sure, sir.
Yeah, sure. Thank you very much, sir, for the information.
20 years back, no?
Sir, that is a fantastic piece of information. Actually, I think everybody listen to that, and we will try to get this book. And I think I will request Professor Prithidipa also to put it in the website about the book so that other students will be able to benefit it, sir.
Yeah.
Thank you so much, sir. And
Amazon.in, they supply it. Amazon.
Okay, sir. Okay, Amazon. Okay, sir. Okay. So with this, actually, is there any other question? I think I have to close down this lecture. Otherwise, we are already running out of time.
It is a nice type of work, very excellent work, taking most of the plants, medicinal plants of Ceylon, and making their experiment on their efficacy as drug. So that is very nice work she has done.
Absolutely, sir. Absolutely. And thanks to Dr. Napagoda for the excellent presentation, and congratulations for receiving the award from the CRS. Thank you.
Thank you very much, sir. Yeah.
Over to Gopal. Yes.
Madam, please close the slides.
Yes. Thank you, Jaisankar sir, for chairing this session, and also very much thank you, Dr. Mayuri ma'am, for delivering your lucid lecture. Now I would like to request the chairperson of this session and the president of CRS to felicitate Dr. Mayuri Napagoda.
So thank you very much, Dr. Morin Apagoda, for your excellent presentation. And society is going to award you this bronze medal and a memento. So please accept this and also this certificate. Thank you, madam.
Yeah, thank you very much for this offer.
Really fantastic work.
Yeah.
Please continue to do so.
Yeah, yeah, thank you. Yeah.
Very nice. Thank you very much.
Yeah, thank you.
Thank you, ma'am, and thank you, sir. Now our next our lecture is by Dr. Subhasis Roy from BITS Pilani, Goa campus. I would like to request Professor Jaisankar Kumar Rai to kindly chair this session. Professor Jaisankar Kumar Rai, sir.
Hi. Good morning, everybody. It is already late, so we will not waste any more time. Straight away, let me introduce today's last, but definitely not the least important, but very important speaker. He is Dr. Subhasis Roy. I know Dr. Subhasis Roy when he was in Vidyasagar University for some times, and we had interacted teaching. And let me introduce in brief about his achievements and studies and different places. He did his BSc honors in chemistry from Bankura Christian College, that is under Bardwan University, and then Master of Science in Chemistry from Vivekananda Mahavidyalaya, that is also in Bardwan University. And after that, he joined Indian Association for the Cultivation of Science, my old place, where from I did my PhD. He also did his PhD, but many, many years later, with a bio-organic chemist, Professor Arindam Banerjee, who is expert in amino acid and peptides and nanomaterials. So after that, he moved to Israel and joined at Ben Gurion University as a postdoctoral fellow under the supervision of Professor Nurit Askamsi. Almost he was there for 3 years, little more, and then as I said, that he moved back to India and joined Vidyasagar University as a GST Inspired Fellow for a few months when I interacted with him. And after that, he moved to BITS Pilani, that's in Goa campus, and he's still there. And he has been exposed to different fields. One very interesting thing is Supramolecular Electronics in Israel, bioorganic material science, that's in ISCS Calcutta, and of course his own field. So it is a combination of several things. He's a good interdisciplinary chemist, I should say. Today he is going to tell us a very interesting thing, that is bio-inspired supramolecular materials for electronic applications. So I will not waste any more time. I now request Dr. Subhasis Roy to deliver his talk. Dr. Subhasis Roy, please.
Yeah, so it's just good afternoon. So good afternoon, sir, for the nice introduction. I am really missing the place. So we have interacted a lot in the HOD office sometimes, you know. So yeah, I'm missing that place. So it's my pleasure it's my pleasure, and I'm honored that you introduced me. So now I would like to go to the talk directly. So before that, I would like to thank the convener, Professor Braja Gopal Bag, and the entire team, the committee for the Chirantan RASAYAN Sanstha, and for this award. I'm really honored and happy. So now I'm just presenting the screen. Please let me know whether it's visible or not. I guess the screen is visible, and you can see it in full screen mode, right?
Yeah, this is perfectly okay. Go ahead.
Okay. Thank you, sir. Thank you. So basically, I will talk about 30 minutes, and if I exceed, if I'm exceeding time, so please let me know. So I will try to complete it within the time frame. So basically, I will talk about today bio-inspired material, and those are of course derived from supramolecular chemistry. I'll talk about, and also I will tell that the electronic application for the total world for now there is a demand for energy, and that demand is from the green energy, basically the material which we can derive from the biomaterial or from the nature. So you can see there is an example I have given, that is a electrical chip used in a mobile which is derived from cellulose nanofibers. So I'll come to peptide nanofibers later on. Just before that, I would like to start the talk with a very good quote from Albert Einstein, sir, that look deep into the nature and then you will understand everything better. So basically, if you are synthesizing a material or a molecule which nature has synthesized, like the Professor Desai and also Dr. Napagoda mentioned that the biomaterials basically. So basically, you can see the biomaterials here. One example is protein, and I will talk about the biomaterial. I will talk about the peptide, which is also a biosphere material. So if you look at the nature, you will see that many interesting molecules are there, and not only that, within the synthesis of those natural molecules, many interesting processes are involved. So all those processes are really interesting. You all must be knowing that in 1800th century, Alexander Volta, sir, discovered the electricity by discovering a electrical battery. But so we came to know that 1800th century, actually 1800 that during that time, that this is the possibility of electricity. Okay, now in 2010, when the discovery of Gopal bacteria came into in a paper Nature, so there people came to know, okay, the filament of this Gopal bacteria actually conduct very nice electricity. So, and this bacteria has been discovered long time back. So now the idea is that the electrical filaments is also synthesized by nature long time back. So the electricity is not discovered in 1800th century, but long time back, and through evaluation, actually we got the such kind of material. So I'm just going to talk about the the peptide based molecule basically. So before describing peptide, we need to know what are amino acids. Amino acids are the building blocks of the peptides. You can see the molecule where you have one amino group, one carboxylic acid group, okay, and it has a CH2, and the hydrogen has been replaced by some R group. So the simplest form is glycine. You must be knowing it. And according to the molecular weight, you can also differentiate between amino acid, the low molecular weight, and when the amino acid coupled together to form a little bigger molecule are peptides, and when they form a giant molecule, or I should say super molecule, is the protein. Now people are, I think you must be knowing very recently. Sorry, I thought I will highlight here. Very recently by Fraser Stoddart, sir, one review came in Nature Material about the super molecule electronics. Today I am not going to talk about super molecule electronics like the protein or the DNA, but I will talk about supramolecular electronics, or the supramolecular material for electronics which are derived from peptides. So you can see that if two amino acids are joined together, they release one water molecule, which is exactly, I mean, there is no hazardous material that during these processes we are generating, and we are getting out of it one peptide. So the peptide can be synthesized using two procedures. One is solution phase, and another is solid phase using resin based chemistry. And on this topic, you must be knowing that Robert Bruce Merrifield, sir, got Nobel Prize in 1984 for synthesizing resin for the synthesis of solid phase peptide synthesis. So this is a alpha helical peptide with a MOC phenylalanine attached to it, and this is the resin. So why these peptides are important? So peptides are important because you see there are various applications of peptides. We all are aware about 3D cell culture, drug delivery. It is applicable to, it is, many peptides are used in bioimaging, biosensor, gas encapsulation, nanofabrication. And you can see there is one, this image has been taken from a review, ChemSoc review, you can see, and here it is mentioned, and more to come. So basically it is a developing field. Okay, many things to come in near future, and of course we all the peptide who are working on this field, they all are hopeful that this you can see that one smallest example, like I said the dipeptide, and this peptide is derived from phenylalanine. You can see. So Professor Visai has also mentioned about chiral, the amino acids which are derived from nature. So here you can see this is the smallest amino acid is phenylalanine, and if you couple to phenyl, you will get to diphenylalanine. And this is the mostly studied peptide in this world, which has very nice morphological control, and most of the peptide chemists work on this peptide. Still, many reports are coming on this peptide. So interesting, this Moiety, and it used to give many, structure, like you can control their patterning, you can align them using electric field, magnetic field, using electric field, and also you can control their dimension. So how it is working? Why the peptide molecules are important? Why they are forming such kind of nice, morphological control? You can control how you can do that. So in order to explain that, I am sure that you must be, I must first, mention that the supramolecular chemistry in the year 1987, Nobel Prize has been given to three person, like I should say three, like you can see this is Jamie Lane, and this is Donald Cam, and this is Pedersen. So the discovery of supramolecular chemistry, after that many years we came actually, and many things discovered. And why this supramolecular chemistry is important? Because the thing is, now supermolecule are also interesting, which Fraser Stoddard sir is developing the field. So you can see, and that he also a Nobel laureate. So the peptide molecules, these are the monomers. Okay, so they can form several supramolecular structures. So these are the supramolecular structure which you cannot synthesize by just in a round bottle flux. If you rotate it, you will, with some solvent and with heat, you cannot make this. So there are some beauty. What are those beauty? Those are the non-covalent interaction which are involving in order to form such kind of structure, which is beta sheet, alpha helix from peptide, and so on, in order to get the supramolecular material, which can be fiber based, which can be tube based, which can be vesicle based, or which can be a filament based like this. Basically, I am going to talk about today mainly this tube, fiber, and filament based material. So these peptide molecules are important because they can self-assemble through using non-covalent interaction, and they can form several supramolecular structure which we can materialize in order to measure the electricity. And in this way, you can see that supramolecular electronics came into picture. So initially, people used to measure the conductivity of a single molecule. There are many reports and there are many studies are going on this. It is also developing. Many studies already reported in this field, molecular electronics. So basically, how you can measure the electricity through a single molecule. So basically, you have one electrode, you have an electrode here, another electrode. If you place a molecule, okay, you can just somehow by any means you can attach within this electrode, and you can have the you are closing the junction. So basically, you are closing the junction with this, and you will have the electricity. So it looks like easy, but it's not easy to measure because there are so many errors that come across, and you have to maintain all those protocols. So basically, you can do it by AFM measurement. You can do that, of course, and this is very interesting measurement. One of the process is break junction method. So you just attach the molecule in this two electrode, you measure the current, and then now break the junction. So basically, you now leave the tip of the AFM, and there will be no more closed circuit, so open circuit, and you will have no current. So that way you can measure it. So that is a single molecule. Now after that, 1D nanostructure came. I mean, if a molecule, let's say if a peptide molecule, let's say this is the peptide molecule, and it is forming a structure like that in one dimension. Okay, like that. So basically, here you have non-covalent interaction, here is non-covalent interaction. This way, no non-covalent interaction, only in 1D it is working, and it can form a structure like that, and you can measure the 1D nanostructure through two electrode, their electricity. Okay, so I'll come to I'll talk about what are the different kind of electronic measurement you can do. Also in 2 dimension you can measure like that. Also in 3 dimension or bulk material, like not in assembled state you can also measure. So why such kind of measurements are important? Why? Because you know that today's world is looking for the, as I mentioned initially, that we need energy, okay, and we need to develop energy through a process which is bio-inspired based chemistry, and which will not generate any toxic material, or which will give our energy in a very with very less cost, okay. So economically it should be very favorable. So in this in order to emphasize this topic here, I would like to tell that proton conduction is one of the best technique to get electricity using fuel cell methodology. So I will come to the fuel cell, but before that, if you have a proton and if you have a material which can conduct the proton through the peptide or through the polar side of the, just a minute, here this is a disturbance for flight, the airport is very near, okay. I think I'm audible, right? Sir, can you please? Okay, thank you.
Please go ahead.
Thank you so much. So you can see that if you have some polar groups, so the proton can transfer from one end to another end. So if a proton is transferring, so this is the active layer basically on a solid surface. Now if you can connect it to two electrode, and if you measure the current, so here the proton is moving, here the electron will close the circuit and we will have the electricity. So the molecule which can allow the proton to transfer, or the material which can allow the proton to transfer through it, they can actually show the proton conductivity. And why proton conductivity is so important? Because the fuel cell, the proton exchange membrane, I will come to that topic, proton exchange membrane, you can use it. Now, proton transfer is very ubiquitous in nature. We all know that in photosynthesis, in natural photosynthesis, you can see natural photosynthesis also, proton here the proton is moving from this side to this side, and we are generating basically ADP to ATP, the energy which is storing in the form of in tree, and they are using this energy. So this energy is getting, but the proton also, as well as in this process electron transfer is also involved. Now, another thing Professor Visai has also mentioned, that the retinal, the change of the cis to trans, which is happening in rhodopsin, also it is happening in bacterial rhodopsin, which is a natural process. And you can see in this 3-dimensional structure, this is the retinal molecule, and with the help of lysine, it is actually getting protonated, and this way the proton is getting transferred from here to here, and and ADP to ATP is synthesizing in this natural processes also. So we all are inspired from the natural process, and this is why these are bio-inspired process. And also I would like to tell one recent report from Rolandi group from University of Washington. They are also extensively working on this proton conducting natural molecule, like the molecule that can be derived from the animal or plant. So you can see this is the skate and this is shark, and they usually detect the prey using this, they can locate the prey using this conducting material. One conducting material is there, and which is a gel-like material. This is known as Lorenzini jelly, and this is called ampule of Lorenzini. That is why this is AOL. And here you have one molecule. That molecule is a sugar-like structure. I am not showing the structure here. So that can actually also conduct the protons, and this is the they actually sorted by this electronic configuration. Here they deposited the jelly. These are the electrodes, and they measure. You can see in between this point and this point, if you touch with 2 probe, and you will have the circuit closed, and you can measure the current. So this is a natural phenomena that is telling that proton conduction is important, not only in in natural processes, and also they are using this proton conduction in order to like in skates they are locating the prey. Now you all must be knowing that the fuel cell. So first I would like to tell that in this diagram you can see this is a fuel cell diagram, and this is one electrode, this is another electrode, and you have a membrane here. So this membrane has a particular characteristic. This membrane can only allow the proton to pass through. So you can see that hydrogen gas is coming, and on this electrode it is breaking to hydrogen plus, H plus. H plus is going through here and it is reacting with oxygen. Further flight again, and the electron is going to this close this circuit and will have the electricity. So and in this case you can see that the hydrogen is reacting with oxygen in order to form the water, which is a byproduct, and that is a completely green material, we all know. So that is why this is very much interesting. So if we can construct a membrane which is very interesting and cost effective and also bio-inspired material. There are reports to construct such kind of conducting material in the. Not only I will come to that topic. Not only that, these are also important in carbon dioxide reduction. So reaction. You can see CO2RR. It's not the you don't read it as ester or something like that. Read as carbon dioxide reduction reaction. I know that all of you must be familiar with this current problem, that the carbon dioxide is increasing, the greenhouse gases are increasing. So we need to reduce all these things using some protocol. And here also using two-cell geometry, using enzyme catalysis or some photocatalytic material, you can there are reports for the reduction of carbon dioxide to some value-added product like methanol, ethanol, formic acid, and here also we need some proton conducting material like Nephyon has been used. So Nephyon is a polymer. You can see Nephyon is a polymer which is very renowned proton conducting material, but this is a polymer. And the problem of this Nephyon, it is really conducting. The problem is it is not stable at higher temperature. Okay, so I can tell that okay, so here you have the humidity. Okay, during the presence of water, it is conducting the electricity. So there is a cost of water also. You need to supply the water to conduct the electricity. So I would like to tell, okay, don't I'm not going to give you water. You need to run this fuel cell without water. That means it will be anhydrous without water. So in order to decrease the cost of the water, so that time this Nephyon is not useful. There are reports, many reports on molecular organic framework. There are many MOF reported in the literature. Those are also very much interesting and showed applicability in order to form the proton exchange membrane. But of course, there are some toxicity from the transition metals, and also conductivity may come from the metal also. There are reports from covalent organic framework of COF. Like after that, MOF, COF is now many people are working on COF, and it's really very interesting topic, interesting field. So here you can see that the imidazole moiety or also triazole moiety, they are actually responsible for these are the heterocycles, and these are the responsible moiety for the proton conduction through a mechanism. I will tell you the mechanism. What is that mechanism? I will come. There are reports from cephalopod animal reflecting protein, and also there are reports from this is a again there is a slide just so this is a tilapia fish, and from the protein of tilapia fish, this is a collagen based protein actually, and this protein has been utilized. The filament of this the filament has been synthesized from this protein and utilized in 3-cell geometry in order to run a digital clock. So these all are there are reports, but the thing is that in proteins or there is a problem in the mutation of the amino acids. So it is also not cost effective. But if we can find out such a material which is really easy to synthesize, and where we can do the mutation of the amino acids, and mutation is really interesting, and it is also required for in many design we all know. So you can see this is the beta 42 amyloid peptide sequence KLVFF. AKLVFF. So in here, 2 alanine has been replaced by 2 phenyl and 3 phenyl moiety, you can see. And they can actually self-assemble to form very nice, you can see, nanotube-like structure. So that is why these linear peptides are really important, because there are so many non-covalent interacting side, like these are responsible for pi-pi stacking interaction. These are for hydrogen bonding interaction, like this way. These are for pi-pi stacking, and also there are some hydrophobic van der Waals kind of interactions are there. So that is why these molecules are important. Using those protocols, these molecules are forming nanotubes. Also the cyclic peptides, like the cyclic DL alpha cyclic peptide, where you have H amino acids and they are alternating D and L. So you must be knowing the work of Professor Gadri. So Gadri is very pioneering in this topic, and I am the grandson. You can tell I am the grandson of Gadri. So I am also working. I have worked with the cyclic peptides actually. Okay, so Nurit is the student of Gadri, and she worked with the cyclic peptide. I also worked with this cyclic peptide. I will come to this topic, and they easily form such kind of barrel-like structure and nanotube-like structure. And we can actually tune the side chain of these nanotubes in order to conduct proton through the nanotube. So I will come to that topic. So how the proton is conducting? As I said, the proton conduction can happen through two type of mechanism. One is vehicle. Like vehicle means, let's say I have a vehicle and I want to deliver a material from one door to another door, or one shop to another shop. So the vehicle is moving with the material. Okay, so that way let's say this is the starting point and this is the end point. So the vehicle is itself coming to move the proton can move through a vehicle. So here you can see in this example, the proton is moving through a vehicle like the imidazole, this moiety, and through triazole moiety. Or it can also move through Brothers mechanism, like the proton can hop from one end to another end. So this is a proton hopping mechanism. Like here, one end you have a polar group. It is accepting the proton, or it can release the proton. It can be through OH minus also proton hole, and it is giving the proton to this polar side. Now from here to here, now this proton is moving, so that way it can move, and this is a proton hopping. And there are many. I will show you the example in a device geometry. This is also from Roland group. So he is also our collaborator. So basically, you can see that here the proton is moving. As I said, the proton is moving through water channel, and these waters are involved with maybe with glucose, with maybe some sugars, with maybe some peptides. You can see some proline kind of amino acids is present here. So proton is moving through this way and through the active layer, and the electron is moving to the outside, and it is completing the circuit, and we'll have the electricity, as I said. So this is the proton moving. How it is proton? So basically, this is happening where the material is donating the proton. So it is a proton rich system, and where the material is accepting the proton. So it is proton hole or hydroxyl kind of system. Here also the proton is moving from one end to another end. So this is the Brothers mechanism, or So here I will talk about a simple peptide. As I said that the amyloid beta sequence AKLVFF. So the question is, if we change one amino acid, if we mute one amino acid, if you want to do the mutation of one amino acid, so like lysine can be replaced by glutamic acid. This is a basic, and this is a acidic amino acid. So can we change the conductivity by changing only one single amino acid? And the answer is yes, we can do that. Of course, you can see. So here it was lysine, then acidic glutamic acid, and also we studied with some neutral amino acid glutamine. Okay, so here you will have no interference. Here we will have proton donation. Here we will have proton acceptance. So here the system will be NH3 plus. Here the system will be carboxylate. Here it will be neutral. So basically, it will be giving the proton to the system. So if it is giving the proton to the system, so we ask the question before measuring that if it is giving a proton to the system, that means proton, and here it is generating a proton hole within the system. So proton hole has higher molecular weight than the proton. So the mobility of the proton hole will be much less than the proton. So the conductivity should be high here. And here, of course, it will be least because there is no ions or there is no proton or proton hole. So we measured in a device geometry, we actually synthesized the nanofibular or nanofilament structure out of the A beta peptide. You can say A beta K, lysine, A beta E, glutamic acid, and A beta Q. And in methanol, and it has been broadcasted in this geometry on gold electrode. I will come to this electrode topic in detail just a minute, just after, in a minute or maybe in 2 minutes. And then it has been studied. This is SEM images on electrode after broadcasting, and you can see there are fibrils, so there are filaments. So if you now touch a probe here and a probe here, and you can close the circuit, you will see the current at different relative humidities. Why I'm talking about different relative humidities? So relative humidities actually, if you see the enhancement of current with humidity, if you are controlling the humidity, if you see enhancement in current, that means you can tell that water is, you are increasing the water within the system, basically increasing the relative humidity. So the proton, basically, if there is any enhancement in current, that means the proton conduction. So that by that you can tell only just very simple experiment, humidity control IV experiment. And this is the resistance has also been measured. You can see the glutamic acid containing the fiber or the filament has a low resistance. Of course, low resistance and the bulk resistivity is also less. But the thing is that here you can see the bulk resistivity ratio is coming under 50. It is almost 51. But if it is only, if we only talk about proton and proton hole, if we only talk about the mobility of proton and proton hole, then it should be 2.7 times. But why this is 51 times? So in order to answer that, we measure not so the proton conduction not only depends on the charge density. It is depends on mobility, as I said. So I already mentioned the mobility terminology. Now we need to measure the concentration, charge concentration. So if there is a technique you can measure by electrostatic force microscopy. It is if it is a multi AFM, like you can measure many kind of measurement using AFM. Then you will have one thing, EFM. And that by means of EFM, we can measure the contrast of the fibers. So where you will see much more contrast, that means here the charge density is also more. That is by phase you can measure it. You can see by phase. And this is the glutamic acid containing peptide is much more contrast. That means here you have much more charge densities. So as you have more charge density in case of glutamic acid peptide, and also the mobility of H plus is more than OH minus. That is why the conductivity for the glutamic acid containing peptide is much more, where you have just mutation you are doing using glutamic acid. So that is why just by single amino acid mutation you can have the better conductivity. Now, in order to measure such kind of proton conduction, whether metallic conducts are good or not, I'm just going to talk about. So basically, as I said, I'll just come to in 2 minutes that I'll talk about electrode. So now I'm going to talk about electrode. What kind of electrode we should take? So this material, we can take gold, we can take palladium, and we can also take palladium hydride for such kind of HX, such kind of measurement. But that when we are measuring electron conduction, when we are measuring electron, then such kind of metallic contacts are good. But when you are measuring proton contact, then whether it's good or not, I will come to that topic. Because you see that there is electrode and there is the material we have broadcasted. So there is the interface. And in between that interface, like you can see the fiber here also. So there is the interface. So there is a gap. So how the proton is converting from one filament to the electrode. So there is a gap. So that means there are some chemical process is occurring at higher relative humidity, and that chemical process is water splitting. I will come to that topic. So you can here also we have studied the proton conduction using palladium electrode, using gold electrode. We saw the palladium electrode is good than the gold electrode, and this is one interesting experiment. As I said, that proton is much more, the mobility is more than proton hole. that is also we can do using the humidity. We can control the humidity using water. We can also control the humidity using D2O. So here also H plus and D plus. So D plus will move less. So if we see when we are measuring the conductivity using water, if we see there is a decrease by replacing H2O by D2O, then that is a proton conduction, and that is the experiment here. You can see that here it's in water, here it's in this is in palladium, and here it's in D2O. So there is a decrease in current, and it is telling the ratio. You can see that in D2O the resistance is more, palladium also more, but less than gold. So that means palladium is a good contact than gold when we are measuring at higher relative humidity. So what does it mean? It means that there are some chemical processes going on irrespective of the metal, and palladium is good in that chemical process. And that chemical process is, I am not talking about this IV characteristic because this is very common, and that is the water spreading. So here in the interface, water spreading is taking place, and you can see that, as I said, depending on the peptide, whether you have basic amino acids or acidic amino acids. If you have basic amino acids, so you will have one procedure. So it will be OH minus will be generating within the system, and if it is acidic, then you will have more acidic proton within the system. So it will be hydrogen evolution reaction, oxygen evolution reaction, or here it will be hydrogen evolution reaction. And in this case, palladium is very good in conducting the protons than gold at higher humidity. But if we talk about lower humidity at vacuum, you can see that gold is very good, because in gold, because there is no proton conduction at lower humidity, only the conduction is electron conduction. And this peptide, you can see in this design, there are some aromatic moieties, so there is possibility of electron conduction, and this peptide conduct electricity at vacuum. I mean electron at vacuum. That has been also identified in a previous literature. I have not shown it here. Now we saw that gold and palladium contacts are very good, and another contacts I have not mentioned. So you can see here. Sorry, I'm sorry. That here the contact resistance, the RC is contact resistance, and this is the bulk resistivity. Okay. So when you are measuring in palladium hydride electrode, palladium hydride is the beauty of palladium hydride is, if you introduce the H2 gas, it will be converting to palladium hydride, and it will be injecting the proton. It will be injecting the proton to the peptide active layer, and it will be again converting to palladium. So basically, this is actually a proton plus proton flux we are actually introducing within the system, and we saw that for proton conduction, PDHX electrode is much better than gold and palladium. But it depends on the you need the hydrogen gas in order to measure this. So very quickly, I will go to another topic, that is this paper is under revision. This is a very interesting topic actually. Basically, many things are studied, but the one basic thing is not yet studied, that what are the fates if we change the side chain of the peptides, or side chain of a cyclic peptide. Now I am going to talk about from let's say histidine to lysine to arginine. That means you are increasing the pKa. So this is a least pKa. Here you have moderate. Here you have maximum pKa. So these are the three basic amino acid has been replaced in this R place. You can see there is a cyclic peptide, and these molecules can from very nice tubular like structure, you can see, and this is a theoretical measurement for hexamer has been shown. So all these three has been studied with proton conducting device, and we measure the proton conduction. These are the antiparallel beta sheet like structure. I'm not going into details. It has been observed that the lysine based peptide filament are most conducting than arginine than histidine. So it is not matching with pKa. So what does it mean? So by theoretical studied, we have established that the lysine, you can see the structure here. The lysine here, it is much more flexible structure. These are not flexible. There is, if you give there is a proton, then the proton is stabilized through resonance here also. but it is more flexible here. The proton is more flexible. There is no stabilization. So that is why, due to the flexibility of the structure, and proton is much more available to move forward. That is why this material is much interesting than the other. And
Subhasis,
yeah,
please conclude very quickly. Huh?
Definitely.
Sorry to interrupt.
No, sir, it's fine. So with this, there is another example, and this is the last example, and I will take maximum 2 minutes. So here you can see that we showed with peptides now how we can grow the lysozyme crystal within a peptide hydrogel. And let's say this is the lysozyme crystal, and this is within a hydrogel. Why hydrogel? I will tell. This hydrogel is helping the carbon nanotube to disperse. So you have the carbon nanotube throughout the gel. Now you are growing a crystal which is lysozyme. When you are growing the crystal, whether the filament of carbon nanotube is growing like this or not, and if it is growing, then can we measure the current if we touch one electrode here, another electrode here by conducting AFM? And that is the beauty of this work. And you can see with the enhancement of concentration of carbon nanotube, the color is also changed of the lysozyme crystal from yellow to black. And when this is the 500 microgram per ml carbon nanotube containing crystal, and it shows really nice IV characteristic in probe station geometry, and this is in conducting AFM geometry. And it says that the entanglement of the carbon fibers from one end to another end is happening, and that is why we have very nice conductivity in conducting AFM. Very nice spot also you can see. And with this, this example is very good, and this is the example of electronic conduction. And currently in my lab, I am working with the versatile supramolecular catalysis in context of origin of life. And also I'm working on proton conduction and so on. So with this note, I would like to thank Professor Arindam Banerjee, School of Biological Sciences, ISCS India, Professor Nurit Askenazi, Department of Materials Engineering, Ben Gurion University, Israel, Department of Chemistry and Chemical Technology, Vidya University, West Bengal, India, Director, BITS Pilani, KK Birla Go-Compass, VC, Sir BITS Pilani, and SRCD BITS Pilani, and all my collaborators, students, funding agencies, and also the fellowship. I got a fellowship during my PhD from CSIR, cultivation of science for my PhD infrastructure, and all the work that I've carried out. And I registered under Jadavpur University. I did postdoc from Ben Gurion University, and also the Friedman Advanced Graduating School. Also, I would like to thank the funding agencies, DST, Inspire, for giving me the faculty award for carried out my research, to carrying my research for 5 years. So it's still going on this project, and also I got funding from BITS Pilani for so, and also currently I'm many grants are also under any reviews. So hope those will be come into picture in future. And with that note, I would like to thank all of you for your patience. And if you have any questions, please feel free to ask.
Okay, thank you, Subhasis. You presented very nicely, a little more than half an hour. So I will not repeat those things again. Very interesting topic. And I forgot to mention one important thing. You wanted to be a very good teacher and inspire the students. You are an inspired fellow, just inspired fellow that time.
Yes,
inspired the students to take up some challenging things, and that reflects in your presentation today, which includes proton transfer to electron flow to whatnot, from simple amino acid to peptide, and then combination of all those things, and getting a really interesting work. So keep it up. I should say it is a very nice work. And if there be some questions you have already asked, students or other members can ask. Otherwise, I will hand over the microphone to Pujo for giving me the opportunity to chair this session. Thank you, Pujo. Thank you.
Thank you, sir. Thank you so much. Thank you, sir. I will try my level best. Thank you.
Yeah, thank you.
Thank you.
Thank you, Professor Kumar Rai, sir, for chairing this session, and also thank you, Dr. Subhasis Roy, for your lecture. Now I'd like to request the chairperson of this session and the president of Chirantan Rasayan Sanstha to felicitate Dr. Subhasis Roy.
Thank you very much, Dr. Roy, for your excellent presentation. Very good start. Well, you have to fight and take it forward. We wish you good luck. Hope,
Thank you.
based upon your achievement, the society has recognized you and offers you this bronze medal and this memento and a certificate. Wish you good luck. Thank you. Good
Thank
start.
you. Thank you so much. Thank you.
Very good. Well
Thank
done.
you. Thank you. Thank you.
Thank you, sir. Now we are going to begin our valedictory session. It will be chaired by Dr. Abhishek Ghosh from Department of Chemistry, Midnapore City College. Dr. Abhishek Ghosh, sir.
Thank you, madam, to hand over. Hello.
Yes, Braja.
Hello.
Please.
Thank you, madam, to hand over the session. I have to thanks at first. Good afternoon, everyone. Honorable guest, Professor Dilip Kumar Maiti, Professor P. Jaisankar, Professor Jayant Kumar Roy, Professor Alokesh Bishoy, Dr. Mayuri Napagoda, Dr. Subhasis Roy, Professor Gopal Bagh, respected President of Chirantan RASAYAN Sanstha and Convener of this webinar, Professor Pradip Ghosh, respected Director of Midnapore City College, Professor Sudipta Chakrabarti, Principal, Midnapore City College, and Dr. Prithidipa Sahoo and all the participants. It is such an honor for me to get the opportunity to thank you all delegates. On behalf of the Chirantan RASAYAN Sanstha and Midnapore City College, I extend a warm welcome to the people in the gathering. I would like to express my gratitude to all the esteemed delegates of the webinar for their presence and contribution to make this webinar a great success. I extend my gratitude to our honorable guest, Professor Dilip Kumar Maiti, Professor P. Jaisankar, Professor Jayant Kumar Roy, to take out time from their busy schedule to grace the event. Also, I extend my gratitude to our honorable speakers, Professor Alokesh Bishoy, Dr. Mayuri Napagoda, Dr. Subhasis Roy, for inspiring and encouraging us in the field of science with their words on this special day. A special thanks to Professor Gopal Bagh and Professor Pradip Ghosh to organize this webinar during this pandemic period. We are also thankful to Dr. Prithidipa Sahoo for her melodious inauguration song, and we have to give a special thanks to all participants because their presence makes this webinar successful. At last, I must thank the organizing team and volunteer for working hard for the past few days to make this webinar successful. Thank you, sir.
Braja কি কথা শুনছো?
Dr.
Braja?
Tanmoyee
কথা
madam.
শুনছো আমার?
Dr.
এই
Tanmoyee
Braja?
Bhattcharjee.
শোনা যাচ্ছে না?
Dr. Tanmoyee Bhattcharjee, could you please hear me?
হ্যাঁ?
Abir, Tumi. Now, Secretary's presentation. Secretary, please continue.
Thank you very much, sir. Honorable Chief Guest, former President of the Indian Chemical Society, Professor Sunil Kumar Tolapatro, Honorable Principal of Midnapore City College, and also the co-host of RASAYAN 9, Professor Sudipta Chakrabarti, Honorable former CS Medal Awardees present here today.
না শুনতে পাচ্ছ না? খুব ভালো ওয়েবিনার হয়েছে।
Abir, please conclude. থেমে যেও না।
As guest to grace the occasion, the speakers in RASAYAN 9, Professor Alokesh Bishoy, Dr. Mayuri Napagoda, Dr. Subhasis Roy, and the chairpersons, Professor Jayant Kumar Roy, Professor Dilip Kumar Maiti, Professor P. Jaisankar, Dr. Abhishek Ghosh, faculty members, research scholars, masters and graduate students from various institutions present here today. Ladies and gentlemen, it's my proud privilege to have the honor to propose a vote of thanks on this occasion. The fifth one-day webinar entitled Science Beyond Boundary Invention, Discovery, Innovation and Society, RASAYAN 9, jointly organized by the Chirantan Rasayan Sanstha and Midnapore City College. I, on behalf of the Chirantan Rasayan Sanstha and the entire fraternity gathered here today, including the media persons, and on my own behalf, extend a very hearty vote of thanks to our honorable speakers for kindly responding to our invitation in spite of their extremely busy schedule. I also thanks honorable guests, Professor Sudipta Chakrabarti, Principal, Midnapore City College, and also the co-host of RASAYAN 9. We are thankful to former CRS medal awardees to be present in this webinar and for their encouragements. We are also thankful to Dr. Prithidipa Sahoo, Visva-Bharati University, Dr. Abhishek Ghosh and Dr. Tanmoyee Bhattcharjee and Mr. Suman of the Midnapore City College, who played a very active roles and are highly instrumental in organizing this webinar. We are also thankful to all the faculty members, supporting staff, students and scholars, media persons present here to make this event a success. Last but not the least, we thank the Google Meet platform, YouTube, for providing such an opportunity to assemble in this manner. Thank you very much to you all.
Thank you very much. Thank you. Thanks to all of you. প্রফেসর তলাপাত্র কিছু বলছিলেন, উনি লোক আছেন? প্রফেসর তলাপাত্র? Okay, perhaps he is not there. So, Professor Jaisankar, thank you very much. What is the time?
Thank you very much. And once again, congratulations to you and Chirantan Rasayan Sanstha.
Well, we have
and keep rocking like this. Keep rocking like this. All the best.
What is the time now, anyways?
Oh, it's around 2:20 in the morning.
Night, so you are getting late in sleeping. Okay, going to bed.
It's okay. It's okay. Thank you. Thank you very much. Bye.
Thank you very much. I hope to see
Bye.
you again. Yeah, and
Hope
thank
to.
all of you.
Thank you all. Thank you all. Bye. Bye.